All right, this is going to be our walkthrough for the homework assignment titled Applications of the Derivative Extra Practice. This is just extra applications of the derivative problems to help you prepare for the midterm. So the first thing we're asked here is to find the equations of tangent and normal lines for this function at the given x value, right? So x equals pi over 8. So in order to find the equation of a line, we always need a point and a slope. So we'll start with f of pi over 8. Which will be the sine of 2 times pi over 8, or the sine of pi over 4, which is root 2 over 2. So the point we're looking at is the point pi over 8, root 2 over 2. And so that's our first thing. Our second thing is we need the slope of the tangent line, which we get from f prime of x. And so f prime of x is just a chain rule problem, so that's just 2 cosine 2x, right? It's sine 2x sine u, right? So it's cosine u times the derivative of u. And so now we want f prime of pi over 8, which will be 2 times the cosine of pi over 4. Well, that'll be 2 root 2 over 2, which is just root 2. So the slope of our tangent line is going to be root 2, which means that the slope of our normal line is going to be negative 1 over root 2, and because they're opposite reciprocals. So our tangent line equation should be y minus root 2 over 2 equals root 2 times x minus pi over 8. Okay, that's just point slope form. And our normal line should be same point, y minus the root 2 over 2, but now equals negative 1 over root 2 times x minus pi over 8. So there are our tangent and our normal lines when x is pi over 8. All right, for our next one here, we have a somewhat more annoying function. We have 2x plus the sine of x cubed. And we want to know the tangent and normal line equations at x equals 1. So first we have to find f of 1. We don't know how to find the sine of 1. So this is just 2 plus the sine of 1, all being cubed. So that's our point. It's 1 comma 2 plus sine of 1 cubed. And then to find our derivative, that's just u cubed. So 3u squared, and then times the derivative of u, which is 2 plus cosine x. Now that's actually even more annoying here. So f prime of 1 is going to be 3 times 2 plus the sine of 1 squared times 2 plus the cosine of 1. Right? So that's our tangent line slope, and our normal line slope is going to be the opposite reciprocal of that. So I'm not going to write all those out, but it's y minus, for our tangent line, right? Y minus the y value, which was 2 plus the sine of 1 cubed, should be equal to that slope, which is 3 times 2 plus the sine of 1 squared times 2 plus the cosine of 1 times x minus 1. At least one part of that was easy. For our normal line, it should be y minus 2 plus the sine of 1 cubed equals, now it's the opposite reciprocal of that, so negative 1 over 3 times 2 plus the sine of 1 squared times 2 plus the cosine of 1, all times x minus 1. All right, for our next one here, again, same idea. So first, let's just find f of 2. All right, so f of 2 will be 2 times 2 is 4, 4 plus 5 is 9, and then divided by 2 squared, which is 4, 4 minus 1 is 3, so we just get 3. Much easier point this time, the point 2 comma 3. Then we will need our derivative here, so we'll take our derivative of this using the quotient rule. So f prime of x is going to be x squared minus 1 times 2, right, v du, minus u times the derivative of v, all over v squared. And I don't really need to simplify it so much. I just need to figure out what this is when x is equal to 2, right? So f prime of 2, well, 2 squared is 4, and 4 minus 1 is 3. So we have 3 times 2 minus 2 times 2 is 4, plus 5 is 9. and then times 2 is 4 again. And then in the denominator, we have 2 squared is 4, minus 1 is 3, and 3 squared is 9. And so if we simplify all that down, we have 6 minus 36. Well, 6 minus 36 ought to be negative 30 over 9, which is negative 10 over 3. So our tangent line ought to be y minus 3 equals negative 10/3 times x minus 2. And our normal line ought to be y minus 3 equals the opposite reciprocal of negative 10/3, which is just 3/10 times x minus 2. All right, our next few here, we're going to be using tangent lines or secant lines to approximate the value of a function. And so as we do this, we have to remember what makes a tangent line an under and overestimate. It's always from the second derivative. So we're going to need second derivatives of all of these things as we go through these next few problems. So we want the tangent line. So just like we wrote the tangent line before, we first need the value of the function where we're finding the tangent line. So we need f of pi over 6, which will be sine squared of pi over 6, or the sine of pi over 6 squared. Well, the sine of pi over 6 is a half, and 1/2 squared is 1/4. So the point that we're talking about is the point y, not y, but just the point pi over 6, comma, 1/4. And now we need the slope of the tangent line. So we need f prime of x. The derivative of sine squared of x is 2 sine to the first, or 2 sine x, times the derivative of sine x, which is cosine x. If you want to make your life a little easier, you can just call that sine 2x, because that's the double angle identity. So f prime of pi over 6 is just the sine of 2 pi over 6, or the sine of pi over 3, which is root 3 over 2. So our tangent line equation is y minus 1/4, y minus the y value, equals my slope, root 3 over 2, times x minus our x value, which was pi over 6. And so this asked us to determine the approximation at pi over 5. So we'll do y minus 1/4 equals root 3 over 2 times pi over 5 minus pi over 6. Well, pi over 5 minus pi over 6, that's, if we get a common denominator of 30, that's 6 pi over 30 minus 5 pi over 30, which is just pi over 30. So we end up with root 3 over 2 times pi over 30, and then plus 1/4. And that is our approximation. Then to find whether this is an under or overestimate, we need a second derivative. So if our first derivative was sine of 2x, f double prime should be 2 cosine of 2x. And if we evaluate f double prime of pi over, we can do it at pi over 6 here, because that's where our x value we wrote our tangent line at. And we can see that this is 2 times the cosine of pi over 3. Right? Well, the cosine of pi over 3 is a positive value, right? It's just positive 1/2. So this is 2 times 1/2, which is 1. 1 is a positive number, which means that this function is concave up, which means that a tangent line is just going to be under the true value of the function, which means that this is an underestimate. All right, for our next one here, we want to approximate the value of 3.1 using a tangent line for 3x cubed minus 6x squared minus x minus 6 at x equals 3. So we'll take our function here and evaluate it for f of 3. Right, so f of 3 is going to be 3 times 3 cubed. So that's going to start off as 81. Right, so we have 81 minus 6 times 3 squared. Well, 3 squared is 9. 6 times 9 is 54. So minus 54. Minus 3 minus 6. Well, 81 minus 54 minus 3 minus 6 is 18. So that's our y value. Then we need f prime of x. So that'll be 9x squared minus 12x minus 1. And we'll evaluate that at 3. Now 9 times 3 squared is, again, 81. So we have 81 minus 36 minus 1. Now 81 minus 36 minus 1 is 44. And so we have a slope of 44. So it'll be y minus 18 equals 44 times x minus 3. And we were looking to approximate the value at 3.1. So we have y minus 18 equals 44 times 3.1 minus 3. Well, 3.1 minus 3 is 0.1. So we have 0.1 times 44, which would just be 4.4. And if we add 18 to that, we get y equals 22.4. And so then to figure out if this is an under or an overestimate, we're going to need a second derivative. So our second derivative, f double prime, is going to just be 18x minus 12. And if I plug in x equals 3 to that, right, we get 18 times 3 minus 12, which doesn't really matter what the exact value is. We know that's a positive number, which tells us the function's concave up, which tells us that the tangent line is, once again, like the last problem, an underestimate. All right, for this next one here, we're going to use a tangent line once again on inverse tangent x at x equals negative root 3 to approximate the value of f of negative 2. And so first we need f of negative root 3. Well, that means we're looking for the inverse tangent of negative root 3. And we should know that inverse tangent, the outputs of inverse tangent are always between negative pi over 2 and pi over 2. So it has to be when tangent equals negative root 3 on that interval. Well, that would be at negative pi over 3, right? So it's really important that you know your trig values for all the unit circle values for all the trig functions, not just sine and cosine, but for tangent and secant and cosecant and cotangent as well. So our y value there is going to be negative pi over 3. And then our derivative, right, f prime of x, to find our slope, should just be 1 over 1 plus x squared. Well, f prime of negative root 3 then is just 1 over 1 plus negative root 3 squared, which should just be 3. So we end up with a slope of 1/4. So we have y minus negative root 3, or y plus root 3, equals 1/4 times x minus, not plus root 3. That's almost put those backwards. So let's go back and fix that, right? That should be y minus negative pi over 3. So y plus pi over 3. Sorry about that. And y minus the y value. So y minus negative pi over 3 equals 1/4 times x minus our x value, which is negative root 3. So x plus root 3. And so if we want to evaluate this when x is negative 2, we'll have y plus pi over 3 is equal to 1/4 of negative 2 plus root 3. And of course, we'll just subtract pi over 3. I don't need to really bother to do anything else with this. We'll just subtract pi over 3 from that. And that is our approximation. Then we want to know if it's an under or an overestimate, so we'll take our second derivative. Well, the second derivative is just going to be f double prime. We'll use the reciprocal rule because it's 1 over 1 plus x squared. It should be the opposite of the constant, which is 1, times the derivative of 1 plus x squared, which is 2x, over 1 plus x squared squared. And what we're concerned about here is whether this is positive or negative. I don't need the exact value. So I just want to know, is this positive or negative at negative root 3? Well, I'm going to have a negative 2 times a negative root 3, which is positive, over 1 plus x squared squared. Well, that's always positive. So this is for sure greater than 0. which tells us this is concave up, which just like the last ones tells us that the tangent line is an underestimate. All right, for this next one, we're approximating the value of f of pi over 5, this time on the secant line of sine squared of x. So this is the same function that we used before, and now we're just going to use a secant line to approximate it instead. So we won't have to really redo all of the work. I'll probably write it back out again, but if you were had already done the previous couple problems, you won't have to redo all the work for these two. So our secant line here, we're just going to need to find the value of f of pi over 4 minus f of pi over 6, and then divide that by pi over 4 minus pi over 6 to find that slope. So f of pi over 4, right, that's the first one I'm looking for. So f of pi over 4 should just be root 2 over 2 squared, right, which is just 2 over 4, which is just 1/2. And then minus f of pi over 6, well, the sine of pi over 6 is 1/2, so you square that, you get 1/4. And then pi over 4 minus pi over 6, we can get a common denominator of 12. Right, that'll be 3 pi over 12 minus 2 pi over 12, which is just pi over 12. And 1/2 minus 1/4 is 1/4. So we have 1/4 times 12 over pi, which just comes out to be 3 over pi. So our slope is 3 over pi. We can choose to use whichever of the 2 points we want to write our secant line equation. It doesn't really matter. I think I'll use the, I don't know, I'll use the one at pi over 4, I guess. Doesn't really matter. So we'll have y minus the value at pi over 4, which was 1/2. So y minus 1/2 equals 3 over pi times x minus, and we use the pi over 4 value, so x minus pi over 4. And so we want to evaluate this at pi over 5. So y minus 1/2 equals 3 over pi times pi over 5 minus pi over 4. Well, pi over 5 minus pi over 4, we should be able to simplify that down. That should be, that's 4 pi over 20 minus 5 pi over 20, so that's negative pi over 20. So we have y minus 1/2 equals 3 over pi times negative pi over 20, which should be y equals, well, the pi's cancel, so we have negative 3/20 plus 1/2. And negative 3/20 plus 1/2 would be negative 3/20 plus 10/20, which would be 7 over 20. Right, so our approximation here is 7 over 20. And we still need to figure out if it's an under and overestimate. So I'll write the derivatives out again, even though we found them earlier, right? F prime of x is just 2 sine x cosine x, which we know is the sine of 2x. And then f double prime of x is 2 cosine 2x. And we already determined that, all of these values, when doubled, everything between pi over 6 and pi over 4, when you double them, you still get a first quadrant angle, right? So f double prime of, we'll say pi over 5, is going to be greater than 0, which tells us this is concave up. And when it's concave up, the secant line will be over the true value of the function on the interval. So we get an overestimate. All right, this time we're going to do the secant line for that same function, 3x cubed minus 6x squared minus x minus 6 on the interval 1 to 2. And then we're going to use that to approximate the value at 1.5. So we need f of 2 minus f of 1 over 2 minus 1 to start with, right? We need the slope. So f of 2, it should just be, let's see here, 3 times 2 squared, so that'll be 3 times 8, which will be 24, minus 6 times 4, which will be 24, minus 2 minus 6, And then we'll subtract from that f of 1, which is 3 minus 6 minus 1 minus 6 all over 1. And so as we simplify that down, looks like we get negative 8 minus negative 3, negative 4, negative 10. So negative 8 minus negative 10 over 1. I guess I don't really need the over 1 there. So negative 8 plus 10 is just equal to 2. So our equation, we can use whichever point we want. Doesn't really matter. I'll use, I don't know, I'll just use the one at 1 comma, what was it? 1 comma negative 10. So we'll have y minus negative 10, or y plus 10, equals 2, our slope, times x minus 1. And if we plug in 1.5 to that, we get 2 times a half. And 2 times a half is just 1. And if we subtract 10, we get y equals negative 9. And we found before that our second derivative here, but we'll take our first derivative again. It's 9x squared minus 12x minus 1. And our second derivative then, which is the one we care about for if it's concave up or concave down, is 18x minus 12. And regardless of what value I pick, any value between 1 and 2, particularly at 1.5, right, f double prime of 1.5 is going to be greater than 0, which tells us this is concave up, which tells us the secant line is an overestimate. And I think this is our last of our tangent secant line problems here. So we want to determine if the approximation for f of 2.2 for this function, and if it's an over or an underestimate. So first we'll start off by finding f of 3. Right, so f of 3, and then minus f of 2 over 3 minus 2. So f of 3 is just 3 plus 1, which is 4, over 2 times 3, which is 6, minus 3, so 4/3. And then minus f of 2, which will be 2 plus 1, which is 3, over 4 minus 3, which is 1, all over 1. So we have 4/3 minus 3. Well, 3 is 9/3, right? So 4/3 minus 9/3 would be negative 5/3. And negative 5/3 over 1 is still just negative 5/3. So there's our slope. I'm going to use the point 2, 3, because that's just easier, I think, than using the point 3, 4/3. So we'll do y minus 3 equals negative 5/3 times x minus 2. And we'll approximate this at 2.2. So y minus 3 equals negative 5/3 times 2.2 minus 2, which is which is positive 0.2. 0.2 is 2/10 or 1/5. So we have y minus 3 equals negative 5/3 times 1/5. Well, I hope we see that the 5's just cancel out. So we have y minus 3 equals negative 1/3. If I add 9/3 or 3 over, we end up with y is equal to 8/3 as our approximation. And then we need our first and our second derivatives here, so we'll find those. So f prime will be done using the quotient rule, so that'll be denominator, derivative of numerator minus numerator, derivative of denominator over denominator squared. Simplifying that out, we're going to have a 2x and we're going to have a minus 2x, so those will cancel. And then we're going to have a minus 3, right? And we're going to have a plus 2, well, a minus 3 and a plus 2, oh, sorry, a minus 2, because that's a minus sign there. A minus 3 and a minus 2 will give us negative 5 over 2x minus 3 squared, which tells us that f double prime of x can be found using the reciprocal rule. So that'll be the opposite of, so I can cancel out the negative, and then the constant, and then the derivative of the denominator, which is 2 times 2x minus 3 to the first times the derivative of 2x minus 3, all over 2x minus 3 to the fourth. And I think it's pretty obvious to see that if I evaluate that at 2.2, I don't need to find the exact value, but if I find what it is at 2.2, all that's going on is a fourth power in the denominator, so that's going to be positive. And 2.2 times 2 would be 4.4 minus 3 is positive. Right, so I have a positive number in the numerator and a positive number in the denominator, which tells me this is concave up, which tells me that a secant line is an overestimate. All right, here we're going to use linearization to approximate the value of the square root of 102. All right, so linearization, again, we'll remind ourselves the formula is f of a plus f prime of a times x minus a. And in this case, f of x is root x. F prime of x then is 1 over 2 root x. The x value we care about is 102, and the a value, which is called the center of approximation, which is the value close to 102 that we can easily evaluate f of x at, should be 100, right? Because we know the square root of 100. So this becomes root 102 is approximately equal to root 100, right, f of a, plus 1 over 2 root 100, and that's f prime of a, times x minus a. Well, 102 minus 100 is 2, so those should cancel. And we're left with 10 plus 1/10, which is, we can say 10.1, or if you want to, you could write that as an improper fraction too, it doesn't really matter. So for our next one here, we're just going to use the linearization formula again. Remembering that, it's f of a plus f prime of a times x minus a. So f of x this time is x to the 1/3, right, or the cube root of x. So f prime of x is 1/3 x to the negative 2/3. Right? And then the x value we care about is 10, and the a value that's close to 10 that we can easily cube root is 8. So this should start out as the cube root of 8 plus 1 over 3 times 8 to the 2/3, that's 1/3 x to the negative 2/3, times x minus a. And so the cube root of 8 is 2, and then we have a 2 in the numerator. In the denominator, we have a 3, and then we have 8 to the 2/3. Well, 8 to the 2/3, we cube root the 8 to get 2, and then we square it to get 4. So we have 2 plus 2/12, or 2 plus 1/6, which should be 13/6. And here we're going to do the fourth root of 14. So our fourth root of 14, well, our f of x is going to be the fourth root of x, or x to the 1/4. So f prime will just be done with the power rule, 1/4 x to the negative 3/4. Our x value is 14, and the a value, the only thing that's pretty close to that we know how to take the fourth root of is 16. Right? The fourth root of 16 is just 2. So the fourth root of 14 should be approximately equal to the fourth root of 16 plus 1 over 4 times 16 to the 3/4 times x minus a, 14 minus 16. So as we just said, the fourth root of 16 is 2. We have 2 plus negative 2 over 4 times 16 to the 3/4. We'll take the fourth root of 16, that's 2, and cube it, that's 8. So we have 2 minus 2 over 32, or 2 minus 1/16. 2 is 32/16, so minus 1/16 will be 31/16. All right, if we want to approximate the sine of pi over 7, our function is clearly going to be sine of x. And our derivative will be cosine of x. our x value is pi over 7, and the thing closest to that I know how to take the sine or the cosine of is probably pi over 6, so we'll go with pi over 6. So we should end up with the sine of pi over 7 is approximately equal to the sine of pi over 6 plus the cosine of pi over 6 times pi over 7 minus pi over 6. And so as we simplify that down a bit, we end up with here sine of pi over 6 is a half. The cosine of pi over 6 is root 3 over 2. And then pi over 7 minus pi over 6, that's 6 pi over 42 minus 7 pi over 42, which would be negative 1 pi over 42. And looks like we just end up getting 1/2 minus pi root 3 over 84. And if you want to, get a common denominator, you can, but I don't really care about that. All right, if we want to approximate the cosine of pi over 8, same basic idea as the last one. F of x, though, is going to be cosine x this time, and f prime of x will be negative sine of x. The x value is pi over 8, and the closest thing to that we can evaluate here is using pi over 6. So we'll do the cosine of pi over 8 is approximately equal to the cosine of pi over 6 plus the negative sine of pi over 6 times pi over 8 minus pi over 6. And as we simplify, that becomes root 3 over 2, right, for our cosine of pi over 6. Sine of pi over 6 is a half, so minus a half. And then probably the best common denominator there is just going to be 24 for pi over 8 and pi over 6. So that'll be 3 pi over 24 minus 4 pi over 24, which will be negative pi over 24. So we end up with root 3 over 2 minus a negative, so plus pi over 48. All right, now we want to approximate the change in the surface area of a sphere if its radius decreases from 6 to 5.9 meters. So the surface area of a sphere is 4 pi r squared, a formula you should know. So to use a differential to approximate this change, we'll just say the approximate change in the area is equal to the derivative, 8 pi r, in other words, the slope of the tangent line, times the change in the radius. Well, our radius starts at 6 and changes by negative 0.1. So our r value is 6, and our dr value is negative 0.1. So well, we end up here with 8 times 6 is 48, times negative 0.1 is negative 4.8. So we have negative 4.8 pi, and this was in meters, and it's squared because it's surface area. Our next one here is approximating the change in the volume of a sphere if the radius increases from 6 to 6.1. So we're going to start with an r of 6 and have a dr of 6.1. So our volume, which is 4/3 pi r cubed, the approximate change in that can be found by doing the derivative, which is 4 pi r squared, times the change in the radius. So our dv is just 4 pi times the initial radius of 6 squared times the dr, which for some reason I said the dr is 6.1, but the dr is not 6.1, right? The dr is just 0.1, right? Because that's how much it's changing. So times 0.1. So sorry about that. Now we just multiply this all out. 6 squared is 36. 36 times 4 is 144. And so times 0.1, 144 times 0.1 will be 14.4 pi, and this time it's inches, and they are cubed because it's a change in the volume. All right, For this next one here, we're going to approximate the change in the volume of a cone if the height increases from 4 to 4.2 feet and there is no change in the radius. So the cone is just getting taller. So the volume of a cone is 1/3 pi r squared h. If we take the derivative of this, right, we get dv equals 1/3 pi, and then the r squared h will become r squared dh plus, using the product rule, 2r dr times the h. And so if there is no change in the radius of the cone, dr is equal to 0, which means that this whole term here just goes away because dr is 0. So all I really care about is r squared times dh. Right? So I have 1/3 of pi times my radius squared times dh. Well, my height went from 4 to 4.2, so dh is equal to 0.2. But I still need an r value to plug in there. So I have to figure out what that actual r value is, right? And so we can't just go and like plug in the h value of 4 into that, right? So what we need to do, actually we don't really need to do anything there. We have no way to find that r value because I didn't give you an actual volume for the original cone. So this is just going to be in terms of the radius. And so 0.2 or 2/10 is 1/5. So we end up with 1/15 pi times the radius squared. So whatever the radius was, right, it's going to change by pi over 15 times that radius squared in feet cubed, right? Because this is a volume of a cone that's in feet. Yeah, for a second there, I thought we'd be able to find that radius, but I didn't give you an initial volume, so no way to do that. All right, our next differentials one here. We're going to have a radius decreasing from 3 to 2.9, so dr is going to be -0.1. And we have no change in the height, which means that dh is 0. So this is kind of going to be the reverse of the last one, right? The derivative is going to be the same, right? dv is going to be 1/3 pi times r squared dh plus 2r dr times h. But this time dh is 0, which means this term is going to disappear. So our change in the volume this time is going to be in terms of the height. So we'll have 1/3 pi times 2 times the radius, which started at 3, which we do have, and then our dr, which we do have, of -0.1, and then our h, which we do not have. So we can cancel out a 3 with a 3, and then 2 times 1/10 should be 2/10 or 1/5. So we have a -1/5 pi h. So -pi h over 5. And this time our units were meters, and it's cubed because it's still volume. And for our last differentials question here, this time the radius and the height of this cone are both changing. So we have the volume is 1/3 pi r squared h, right? This time r is 6 and dr is 0.1 and h is 10 and dh is 0.2, right? Because we've got all of these changes this time. So our derivative should be the same as the last two problems, 1/3 pi times r squared dh plus 2r dr and h, right? Just using the product rule. So now we just plug everything in. We actually have everything this time. So 1/3 pi times r squared, so that'd be 36, times dh, that's 0.2, plus 2 times r, which is 6, times dr, which is 0.1, times h, which is 10. Well, right off the bat, 1/10 times 10 should just cancel out. So we can get rid of those. And then we end up with let's see, we end up with 1/3 pi times 36 times 2/10, or 36 times 1/5 should be 36 over 5. And then plus 12. Well, if I want to get a common denominator there, that'll be 60 over 5. So we end up here with 1/3 pi times 96 over 5. Well, 96 over 5 is 32. Oh, sorry, 96 over 3 is 32. So we end up with 32 pi over 5. And this time our units were inches, cubed because it is volume. So for our next ones here, we're looking to find the intervals when the function's increasing or decreasing, where it's got local and absolute maxima and minima, points of inflection, and when it's concave up and concave down. So step one is just going to be to take the derivative here. So our first derivative here is f prime of x is equal to 6x squared minus 6x minus 36, just using the power rule. And then we'll set this equal to 0. And when we set this equal to 0, we should be able to see that we can divide everything by 6. So we'll end up with x squared minus x minus 6 is equal to 0. And then we'll just factor this, right? This factors into x minus 3 times x plus 2 equals 0, which gives us two critical values, x equals 3 and x equals -2. And so what we'll do first is we'll make a sign chart with this. And we'll put -2 and 3 on our first derivative sign chart. And then we'll plug in some number between those, like 0, into our derivative, into the factored form of our derivative here. Right? And so if we do that, when we plug in 0, we get a -3 times a +2, which is a negative times a positive, right? Negative times positive gives you a negative, which tells us the function is decreasing on that interval. And we'll do the same on each of the other intervals. So like if we plug in something more than 3, like a million, then x minus 3 is positive and x plus 2 is positive. So we have a positive times a positive, which is positive. And if we plug in something like -1 million, the x minus 3 is negative and the x plus 2 is negative, and a negative times a negative is a positive. So we can see that our function increases, then decreases, then increases again. So we can see we have a local max and a local min. What the local max is at x equals -2, the local min is at x equals 3. But we don't know if they're absolute maxima or minima yet, and the only way we can really figure that out is by checking the in behavior. So we know, we should know what this is doing. It's a cubic, but if we check the limit as x approaches infinity, the 2x cubed dominates, right? And so we just end up with infinity. And if we look at the limit as x approaches -infinity of this function, well, the x cubed still dominates, and -infinity cubed is -infinity. So we know this function is going down to -infinity and up to +infinity, which means it's not going to have an absolute max or an absolute min. So we'll start with that. We'll say there's no absolute max or min. Okay. We do have a local max at -2, so we do need to find f of -2. So you can just plug in -2 to that. -2 cubed is -8, times 2 is -16, and then -2 squared is 4, times 3 is 12, so -16 minus 12, plus, because it's -36 times -2, so plus 72, and then plus 3. Looks like that, what is that come out to be? That comes out to be 47. We add those all together. And then we'll look for f of 3. F of 3 ought to be 3 cubed, which is 27, times 2, which is 54. And then minus 3 times 3 squared, so 3 times 9 is 27. Minus 36 times 3, which is -108. Plus the 3. And it looks like, let's see, that's 27. Plus 3 is 30, minus the 108 is -70. So it looks like we have a local max of our value at f of -2, right, which is 47. So a local max of 47 at x equals -2. And we have a local min of negative 78 at x equals 3. And we can say that we are increasing on the interval from negative infinity to negative 2, and then again from 3 to infinity. And we are decreasing on the interval from negative 2 to 3. So second part of this problem then is the points of inflection and when is it concave up and concave down. So for that, we'll just need to take the derivative. We'll take the derivative of our f prime, right? So we'll take the second derivative here. So if f prime of x was equal to 6x squared, is that what it was? It was 6x squared minus 6x minus 36, then our second derivative should be equal to 12x minus 6. And then from there, we can just set that equal to 0. And that's true when x is equal to 1/2. So we'll make a sign chart of our second derivative with 1/2 on it. Something less than a half would be 0. That makes this negative, right? 0 minus 6. And something more than a half would be like a million. 12 times a million minus 6 is positive. So we do have a change from concave down to concave up at 1/2. So we can say we're concave up from 1/2 to infinity. And we're concave down from negative infinity to 1/2. And we have a point of inflection when x equals 1/2, so we need to evaluate our original function, right? And our original function was f of x is equal to 2x cubed minus 3x squared minus 36x plus 3. We want to find what that is at 1/2. So 1/2 cubed is an eighth, and 2 times 1/8 would be 1/4. So we have a fourth. Then we have minus 3 times 1/2 squared, so that'd be minus 3/4. And then, let's see, so then we'll have minus 18, and then plus 3, so a fourth. Minus 3/4 would be negative 2/4, or negative 1/2. And we're going to subtract essentially 15 from that, so negative 1/2 minus 15 ought to be negative 31/2. So our point of inflection is the point 1/2 negative 31/2. And that covers everything we were asked to find in that problem. All right, for our next one here, we're doing the exact same thing, just with a 4th degree function. So we'll start off with our derivative, right? F prime of x should be 4x cubed minus 18x squared plus 24x, just using the power rule there. We can factor out a 2x from all of those terms. So we'll have a 2x times 2x squared minus 9x plus 12. And then we should be able to factor, hopefully, what's inside of there, 2x squared minus 9x plus 12. So we try and factor that. Well, actually, we actually look at that a little more carefully. I don't think that factors at all. In fact, I don't think that has any real solutions, right? If we look at that, negative 9 squared minus 4 times 2 times 12, right? That's b squared minus 4ac. That's the discriminant, right? Yeah, which tells us how many real solutions it has. That's 81 minus 4 times 2 is 8, and 8 times 12 is 96. That's negative, right? So our discriminant is negative, which means there's no real solutions here. So we're not going to be able to factor that. And we're not going to get any real solutions from it. So and in fact, we also know that that is always, actually, we don't need to worry about that yet. So we can see that this is equal to 0 when 2x is equal to 0, right? And so that would mean that x is equal to 0. So our sign chart is just going to have 0 on it. And as I was starting to say a second ago, 2x squared minus 9x plus 12, since that has no real solutions, that means it's not going to cross through the x-axis ever, which means it's either going to always be positive or always be negative. Well, if it's concave up, we know it's concave up because it's a parabola with a leading coefficient that's positive, right? It's got to be concave up, which means it's got to be above the x-axis, which means that this thing here is always going to be greater than 0. So when I make my sign chart, we can just treat that as if it's always a positive. And therefore, when we plug in a positive here, we get 2x, which is positive, times a positive. And when we plug in a negative, we get 2x, which is negative, times a positive, so we get a negative. And therefore, our function decreases, and then our function increases, which means that we have a local and, in fact, an absolute minimum here, right? It must be an absolute min because we've decreased, and then we've increased afterwards. So we should find f of 0. F of 0 is just -4. And so we can say we have a local and absolute min of -4 at x equals 0. And we should also be able to say then that there is no absolute or local max because there's no places where this function changes from increasing to decreasing. And we'll just say that we are increasing from 0 to infinity and decreasing from -infinity to 0. So that takes care of the first half of this problem. The second half, we'll need to find a second derivative. So starting with f prime of x, which was 4x cubed minus 18x squared plus 24x, we'll find our second derivative, which will be 12x squared minus 36x plus 24. We'll set that equal to 0. And we can take a 12 out of that, right? It's 12 times x squared minus 3x plus 2, or 12 times x minus 2, x minus 1, which gives us x equals 2 and x equals 1 as possible points of inflection. So we'll make a sign chart using 1 and 2. If we plug in something more than 2 to this, like a million, we have the 12, which is always positive, so I'm going to ignore that from now on. But then we have another positive and another positive, so it's positive. If we plug in something like 0, right, below 1, we have a negative and a negative, so that's positive. And if we plug in something like a half, or a 1.5 between 1 and 2, right, we get a negative and a positive, which makes a negative. So we know that our function is concave up on the interval from -infinity to 1, and then again from 2 to infinity. And it's concave down on the interval from 1 to 2. And then we have points of inflection at x equals 1 and at x equals 2. So we do need to go back to our original function, right? Our original function was f of x equals x to the 4th minus 6x cubed plus 12x squared minus 4. And look for f of 1 and f of 2. Right? F of 1 should just be 1 minus 6 plus 12 minus 4. So that should be 3. Right? -5 plus 12 is 7. 7 minus 4 is 3. And then f of 2, well, 2 to the 4th is 16. And then 6 times 2 cubed is 48, so minus 48. And then plus 2 squared is 4 times 12 is also 48, so those will cancel out, and then minus 4. So it looks like we end up getting 12. So our points of inflection are the points 1, 3, and the point 2, 12. All right, for our next one here, we're just looking for all the same stuff, but for x, e to the -x, right? Increasing, decreasing, local and absolute max and min, as well as concave up, concave down, and points of inflection. So we, again, start off with a first derivative here. So our first derivative here, f prime of x, we'll just use the product rule. So that'll be x times the derivative of e to the -x, which is e to the -x times -1. So we have -x e to the -x plus the derivative of x, which is 1, times e to the -x, which just gives us e to the -x times -x plus 1. And when we set that equal to 0, we see that the only solution that we get there is x is equal to 1, because e to the -x is always positive, right? E to any power is always a positive number. So we don't have any times when that's equal to 0. So we'll just make our sign chart here with 1 for f prime. And if we plug in something more than 1, like a million, we have negative a million plus 1, which is negative, times e to the negative x, which we already said is always positive, so that'll be a negative. And then plug in something like 0, you get positive 1 times a positive, so that's positive. So we can see that f increases, then f decreases. Which means that if we increase and then we decrease, we must have an absolute max at 1. So we'll find f of 1, right? And f of 1 in our original equation is just 1 times e to the negative 1. Right? E to the negative 1 is just 1 over e if we prefer to write it that way. So that's our absolute and our local max. And since it increases then decreases, we don't have an absolute or a local minimum. So we'll start with that. No absolute or local min. We have an absolute and a local max of 1 over e at x equals 1. We are increasing on the interval from negative infinity to 1, and we are decreasing on the interval from 1 to infinity. And then from there, we can take our second derivative. So we'll take our second derivative, which is just the derivative of e to the negative x times negative x plus 1. So that'll be e to the negative x times the derivative of negative x plus 1, which is negative 1. And then plus the derivative of e to the negative x, which is, as we said a second ago, it's negative e to the negative x. And then times the negative x plus 1. And if we factor out the e to the negative x from this again, or we could take out a negative e to the negative x, doesn't really matter either way. I think I'll take out just the e to the negative x. So this is e to the negative x, and then we have a negative 1, and then we have minus the negative x plus 1, which will become e to the negative x times, well, a negative 1 minus a 1 is going to be a minus 2, and a negative negative x is going to just be a positive x, so we have e to the negative x times x minus 2. So we kind of ran out of room down there, that's okay. We've got e to the negative x times x minus 2 equals 0 when x is equal to 2, right? Because that's always greater than 0, just like before. So we only have one possible point of inflection, that's at x equals 2. And we'll make a sign chart using x equals 2 for our second derivative. And if we put in a positive number to that, like a big positive, like a million, we get a positive times a positive, so we're concave up. If we put in something like 0, we get a positive times a negative, which is negative, which means we're concave down. So we can say that we're concave up on the interval from 2 to infinity, and we are concave down on the interval from negative infinity to 2. And then if we just find f of 2, we know what our point of inflection is, right? F of 2 is just 2 e to the negative 2, or 2 over e squared. So we can say that we have one point of inflection. It's the point 2, comma, 2 over e squared. And that is it for that problem. Right, for our next one here, we're again just finding when this function's increasing and decreasing. It's local and absolute maxima minima, and when it's concave up and concave down, as well as points of inflection. So the first thing we're going to do for this one is recognize that it's a little different than the previous three problems because it's got some restrictions on its domain. So before we do any major work with the derivative or the second derivative, let's take a look at the domain of this function. So first off, we know that we can only take the natural log of things that are positive. So we need x cubed minus 3x to be positive. That's our domain, which means that x times x squared minus 3 needs to be positive. Well, that means that this could potentially change signs at anything that makes this equal to 0, which would be 0, or positive or negative root 3. So if we do a sign chart with our original function, we can find the domain. So if we plug in something more than root 3, like a billion, we get a positive x and a positive for x squared minus 3, which means that our function is positive out there, greater than root 3. If we put in something between 0 and root 3, for example, 1, we have, in the original function, we'll have 1 times 1 squared minus 3, which is a positive times a negative. So our function is negative. That x cubed minus 3x is negative there. Meaning our function is not defined between 0 and root 3. And if we plug in something like negative 1, right, then we have a negative for the x and a negative for negative 1 squared minus 3, which makes a positive. And if we plug in something that's less than negative root 3, like negative 1,000,000, the x is negative, but this term, x squared minus 3, is positive, so we end up with a negative. Which tells us that the domain of this function is just from negative root 3 to 0, non-inclusive, right, because it can't equal 0, as well as root 3 to infinity. So anytime we are looking for critical values or points of inflection or anything like that, or possible points of inflection, we have to make sure that we only think about these values for our domain. So with that sort of off to the side and in the back of our heads, we're going to take our derivative now. So f prime of x should be equal to, well, it's natural log of u, so it's 1 over u, times the derivative of u, which is 3x squared minus 3. And so as I look at that, the first thing I want to think about here is what makes this undefined. And so the things that make it undefined are the things that make the denominator 0, right? Well, that denominator, x cubed minus 3x, is what we just found the things that make it 0. And none of those things are in the domain of the function. So I don't really need to worry about those as potential maxima or minima, as potential critical values. I do need to put them all on my sign chart because the function could change from increasing to decreasing or vice versa at those points, but they're not possible critical values. Right? So we could say x equals 0 and positive or negative root 3. We'll say they are not critical values because they're not in domain. But we will still put them, like I said, on the sign chart. Now, for when does this equal 0? Well, that would be when 3x squared minus 3 equals 0. Well, that will be, if we take out the 3, right, it's 3 times x squared minus 1 equals 0, or 3 times x plus 1 times x minus 1 equals 0. And we get negative 1, and we get positive 1. But we're going to immediately eliminate positive 1. This is not in the domain, and therefore it is not a critical value, and we don't need to even worry about it. So when I make my sign chart, I'm going to put all of my values where our function has sort of cutoffs on its domain, and I'm also going to put my critical value of negative 1 because that one did fall right between negative root 3 and 0. So that one is a critical value. So we've got a sign chart that includes negative root 3, and then negative 1, and then 0, and then again root 3. But this part between 0 and root 3, we're just kind of going to exit off because, and in fact from less than negative root 3, we're going to X that off too, because our function doesn't exist there. So we do need to figure out when it's increasing and decreasing, so we need to test stuff on the 3 intervals that we do have. And so first we'll start with something like 1,000,000. If I plug in 1,000,000 to my derivative, right, I have positive 3 times a positive, which is going to mean it's positive, which means my function is going to increase on that root 3 to infinity interval. If I plug in something between 0 and negative 1, let's say, for example, negative 1/2, negative 1/2 is going to give me a 3, which is positive, times negative 1/2 plus 1, which is positive, times negative 1/2 minus 1, which is negative. So we're going to be negative on that interval. And then we'll also need to do the negative root 3 to negative 1. So something in between there would be like, let's say, negative root 2. Right? So negative root 2, if I plug that in, we have positive for 3. Negative root 2 plus 1 is negative. And negative root 2 minus 1 is negative. So it's all positives in there, which means the function is increasing. So we now know what our function does. It increases, then it decreases, then it increases. But we know that we're not actually looking at any endpoints here because our function is not actually defined at negative root 3 or at 0. But we do need to see if it's like going towards infinity there, which we should be able to tell that it is, right? Because if I plug in something like, let's say, negative root 3, right? If I try to look for the limit as x approaches negative root 3 from the right-hand side of my function, I'm going to get, well, negative root 3 squared is, if I'm plugging this in, to my original function, negative root 3 cubed, right? As we think about this, like that value, negative root 3 cubed is 3 root 3, and the same, or so it's negative 3 root 3. And if I put in the negative root 3 into the 3x, I get minus a negative 3 root 3. So I get the natural log of 0. But what it's doing is it's approaching that 0 from the right-hand side, which means that this thing is going down to negative infinity. And the same thing is going to be happening if I plug in 0 into this, right? Because 0 cubed is, you know, as I approach 0, right, we'll write this out. The limit as x approaches 0 from the left-hand side of f of x is also going to be negative infinity. Because as I approach 0, then x cubed is approaching 0, and the 3x is also approaching 0, but we're really doing that, we're approaching that 0 from the right-hand side as I like do a substitution on x cubed minus 3x, because we end up with a smaller negative and then plus a bigger negative, or sorry, minus a bigger negative, which ends up being a positive number that we're approaching 0 from. So we can see that we're approaching negative infinity on both of those, which means that we're not going to have any minima for sure, even though we could have known that already. And then as we should look at the limit as x approaches infinity as well, which we're kind of running out of room for, but the limit as x approaches infinity, well, x cubed is infinite and it dominates, so we're just going up towards infinity as x approaches root 3, right? And so this tells us that this point at negative 1 is not an absolute maximum, it's just a local maximum. And knowing that we're going down to negative infinity tells us there's certainly no minimum, even though we could probably have guessed that from our sign chart because there were no endpoints. So, kind of ran out of room here. But we do still need to find f of negative 1. So we'll write this out. F of negative 1 is the natural log of negative 1 cubed, which is negative 1, minus 3 times negative 1. So negative 1 minus negative 3, and negative 1 minus negative 3 is just 2. So f of negative 1 is the natural log of 2. So on our next page, we'll say that we are increasing, and the interval on which we were, there was a couple intervals on which we were increasing. It was negative root 3 all the way till negative 1. And then it was again from positive root 3 to infinity. And note that I'm using the parentheses on the root 3s because they're not actually in the domain, even though the College Board likes you to use brackets. Normally you would use a bracket if it's included in the domain, but those ones are not, so we won't. Then we're decreasing from negative 1 until we get to 0, and negative 1 is an included point, but 0 is not in the domain, so we'll leave that as just in a parenthesis. And then we have a local max of ln2 at x is equal to, it was at negative 1. And we have no absolute max. And we have no absolute or local minimum. So now we'll need to do stuff with the second derivative to figure out any points of inflection. So if f prime of x, for f prime of x, we had 3x squared minus 3 over x cubed minus 3x. And so now we want the second derivative, so we'll have to find that using the quotient rule. So that'll be x cubed minus 3x, the denominator, times the derivative of the numerator minus the numerator times the derivative of the denominator, which will be 3x squared minus 3, all over the denominator squared. And then we'll have to do some simplification here, of course. So 6x times x cubed will be 6x to the fourth, and then a minus 18x squared, and then 3x squared minus 3 times 3x squared minus 3 with a minus sign in between, right? So that'll be minus the 9x to the fourth, and then the negative 3 times the 3x squared is a negative 9x squared, and then we have another negative 9x squared, which is a negative 18x squared, but then it's got the minus sign in the middle, so plus 18x squared. And then we have a negative 3 times a negative 3, which is 9, so then we have a minus in the middle, so that's minus 9 over our x cubed minus 3x squared. And then we can simplify this down here. So we end up with negative 3x to the fourth, it looks like, minus 9 over our x cubed minus 3x squared, right? The 18x squared terms just cancel out. So we have negative 3x to the fourth minus 9. If we try to set that equal to 0, we get negative 3x to the fourth equals 9, or x to the fourth equals negative 3. Well, that has no real solutions. So we could see that there are going to be no points of inflection for this, right? Because there's not going to be any places where this function is equal to, or where the derivative is 0 or undefined. I mean, it is undefined, right? It's undefined at those same values, right? That made x cubed minus 3x1 undefined before, plus or minus root 3 and 0, but none of those are in the domain, so they can't be points of inflection. So we have no points of inflection, so we'll go back to here. We have no points of inflection. Add that to our list. But we should still make a sign chart using those values, right? So we can kind of cap it off here at negative root 3, here at 0, and then here we don't have anything, right? That wasn't part of our domain, and then root 3. And so if I plug in something like negative 1 into my second derivative, right, that denominator is always going to be positive. But if I plug in negative 1 to the numerator, negative 1 to the fourth is positive 1. Right? And then negative 3 times that is negative, and then subtract 9, it's still negative. And if I plug in something more than root 3, like a million to the fourth times negative 3 is a really big negative, and subtract 9, it's still negative. So our function is concave down for its entire domain. Okay. So we could say that this is never concave up, and we can say it's concave down on our full domain, which was negative root 3 to 0, and again from root 3 to infinity. And that's it for that one. All right, this is our last one on this assignment of the finding the intervals, which it's increasing and decreasing. With the maxima and minima and concave up, concave down points of inflection. So we'll start off just by noting that there is a domain restriction on this at 2, right? X can't be 2. So our domain is just going to be negative infinity to 2 to infinity. So as we go through this problem, we need to include 2 on all our sign charts, but we're not going to have any points of inflection or maxima or minima at x equals 2. So always check your domain first. F prime of x should be, our derivative here is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared, right? Because that's quotient rule for a quotient of 2 functions. If we simplify that out, we're going to get 2x squared minus 4x from the first terms, and then minus an x squared minus a 5 over our x minus 2 squared, which gives us just x squared minus 4x minus 5 over x minus 2 squared. And we can continue factoring that. All right, so if we factor that out, that's going to be x minus 5 times x plus 1 over x minus 2 squared. And we know that this is undefined when x is 2, but that's not a critical value. It'll still go on our sign chart, but it's not a critical value. But this equals 0 when x is 5 and x is -1. So our sign chart will include 3 values, right? So our sign chart's going to have 3 values. Our smallest of those was -1. Our discontinuity was 2, and 5 was our other critical value. So these 2 are critical values, but 2 is not a critical value. So we'll make our sign chart by plugging in values into our derivative that are on each of these intervals. So we'll start with the easiest. Between -1 and 2 would be 0. And we'll note that this thing down in the denominator is always positive, so I don't really need to worry about it for any of the things I plug in. And so if I plug in 0 to the numerator, I just get -5 times 1, which is negative. If I plug in something between 2 and 5, like let's say 3, I get a negative times a positive in the numerator. Well, that's still negative. If I plug in something more than 5, like 1,000,000, I get 2 positives, which is positive. And if I plug in something like -1,000,000, I get 2 negatives in that numerator being multiplied, which makes a positive. So we can see that our function is increasing, then decreasing, then it continues to decrease, and then it increases again, right? So it's decreasing there at that asymptote of x equals 2. So we do have a maximum at -1, and we do have a minimum at 5. But if we look at the end behavior here, like what's happening, the limit as x approaches 5 of f of x, well, that's a faster infinity over a slower infinity, right? So that's just, sorry, I don't know why I said 5. The limit as x approaches infinity of f of x, right? That's an infinity over an infinity. But the top one is going faster, so that's just infinity. And as I go towards negative infinity, we end up with negative infinity squared, which is positive infinity, over negative infinity minus 2, which is negative infinity. Again, recognizing that the top one is faster, which means this is now negative infinity. So we know that we're not going to have any absolute maxes or absolute mins because our function goes up to infinity and it goes down to negative infinity. So we do need to find f of -1 and f of 5 to find out what the actual local maxes and mins are. So if I put in -1 to that, -1 squared is 1, and 1 plus 5 is 6, and 6 over -3 ought to be -2. And if I plug in 5, I've got 5 squared plus 5, which is 30, over 5 minus 2, which is 3. So we end up with 10. And so we've got our intervals here on which we're increasing and decreasing, and we have our local extrema. So we'll write those out. We are increasing. We're increasing from the interval from -infinity to -1. And then we are increasing again on the interval from 5 to infinity. And then we were decreasing from -1 to 2, and the 2 is going to go in the parenthesis because it's not in the domain. And then it's still decreasing from 2 to 5. But the 5 and the -1 go in brackets because that's how the College Board likes the endpoints of increasing and decreasing intervals. And we said that there was no absolute max or min because we checked the end behavior. And then we had a local max of, let's see, our local max was the one at -1, and so that was the what value did we get for that? I think we got -2. Let's check that. Yeah, we got -2 at -1, so we have a local max of -2 at x equals -1, and we have a local min, and that one was 10 at x equals 5. And so now we'll just go through and find our second derivative to find all the stuff that we can find from there. So remembering that our first derivative, probably the easiest form to take the derivative of our first derivative would be when it was x squared minus 4x minus 5 over x minus 2 squared. So f double prime of x should be the denominator, x minus 2 squared, times the derivative of x squared minus 4x minus 5, which is 2x minus 4. So v du minus u times the derivative of the denominator, which will be 2 times x minus 2 to the first, and then times the derivative of x minus 2, so just that, all over x minus 2 squared, so x minus 2 to the fourth. And we can cancel out some x minus 2's here. So I'm just going to have the x minus 2 squared is just going to become an x minus 2 times a 2x minus 4 minus an x squared minus 4x minus 5 times 2. Right? That other x minus 2 is going to cancel with the x minus 2 in my denominator. Right? So I'll just have an x minus 2 cubed there. And now we should be able to simplify this even further. So this will become 2x squared minus 8x, right? Because we have a minus 4x and another minus 4x. So minus 8x plus 8. And then minus 2x squared. And then a plus 8x. And then minus negative 5 is positive 5 times 2 would be a plus 10. All over x minus 2 to the third power, which actually most of that just cancels out. All we're left with is the constants. 8 plus 10 is 18. We have 18 over x minus 2 cubed, which is undefined if x is 2, but we recognize we can't have a point of inflection there because that's not in the domain. And this never equals 0 because the numerator can never be 0, and the numerator is 18. So our sign chart's just going to include the value here at 2 for our second derivative test to see if it's concave up or concave down on each side. If I plug in something like 0 to it, I get 18 over a negative cubed, which is negative. And if I plug in something more than 2, like a million, I get 18 over a positive cubed, which is positive. So we can see we're concave up from 2 to infinity, concave down from negative infinity to 2, and there is no point of inflection. So we'll say no point of inflection. And we are concave up on the interval from 2 to infinity. And we are concave down on the interval from negative infinity to 2. So the next set of problems that we're going to look at here are going to be motion problems, right? So we're given a particle that's moving along the x-axis for t greater than 0 with this position function, and we want to find the velocity of this the first time it's at the origin. So the first step is to figure out when it's first at the origin. That would be when its position, or t squared minus t times e to the negative t, is equal to 0. Well, e to the negative t is always greater than 0, so I don't need to do anything with that. This factors to t times t minus 1, which gives me t equals 0 and t equals 1. Well, it says it's moving along the x-axis for t greater than 0, which means I'm going to ignore this. And the first time that this thing is at the origin would be at t equals 1. So we just want to find the velocity when t is 1. So to do that, we need the velocity function. The velocity function is just the derivative of the position function. So we'll find that derivative using the product rule, right? It'll be t squared minus t times the derivative of e to the negative t, which is e to the negative t, times the derivative of negative t, which is negative 1. And then we'll add to that the derivative of t squared minus t, which is 2t minus 1, times e to the negative t. And so we can simplify that down if we want to, but really all it's asking us to do at this point is to evaluate it at t equals 1. So if I evaluate this at t equals 1, well, the t squared minus the t here, this is just 0. So 0 times negative e to the negative 1, that's just 0. And then 2t minus 1 would just be 1 when t is 1. So we have 1 times e to the negative 1, or 1 over e. So it looks like we just end up getting 1 over e is the velocity at the first time that this is at the origin. For part B, we want to find the velocity of the particle at t equals 3. Well, we've got the velocity function now, just plug in 3 to it. So v of 3 is just going to be 3 squared minus 3, so that'll be 9 minus 3, which is 6. So we have 6 times negative e to the negative 3. And then plus, we've got 2t, which is 2 times 3 is 6, minus 1 is 5, so plus 5 e to the negative 3. So we have negative 6 e to the negative 3 plus 5 e to the negative 3, which would just be negative e to the negative 3. Part C asks us something similar. It says find the speed. Well, we need to recognize that speed is always the absolute value of the velocity, right? And if our velocity is negative e to the negative 3, well, we just need the absolute value of negative e to the negative 3. And e to the negative 3 is a positive number, so negative e to the negative 3 is a negative number, so the absolute value of it should just be the positive version of it. The speed is just e to the negative 3, or 1 over e cubed if you prefer that. So we now move on to same problem here, but we want the acceleration. So our acceleration, right, ought to be the derivative of our velocity. Well, our velocity function, we didn't really simplify it before, so let's do that now. We'll go back actually to this last page. If we simplify this right here, we can factor a e to the negative t out of it. And so if I factor e to the negative t out of that, I'm left with a negative t squared minus t plus a 2t plus 1, which gives me e to the negative t times negative t squared, and then that's the negative t squared, and then a positive t plus a 2t should be plus 3t plus 1. So that's actually what our velocity function was. So let's bring that over here to where we're working here. V of t was e to the negative t times negative t squared plus 3t plus or minus. Is it plus minus plus 1 or minus 1? We had a 2t plus, oh, it was a minus. I wrote a plus, but we actually had a minus there. Right? We had a minus 1 there. I just copied it down here as a plus 1. So we fixed that now. So that's a minus 1. So minus 1. So now we want the derivative of that. We'll just use the product rule. So it's e to the negative t times the derivative of negative t squared plus 3t minus 1, which is negative 2t plus 3. And then we'll add to that the derivative of e to the negative t, which is negative e to the negative t, times the negative t squared plus 3t minus 1. And so then we just need to, we don't really need to simplify it. We can if we want to. Might as well, I guess, just to make things a little bit easier to deal with here. So we'll factor out the e to the negative t. We're left with negative 2t plus 3. And then we're left with plus a negative of everything that's in there. So plus t squared minus 3t, and then plus 1. Okay. And so to simplify that out, we end up with e to the negative t times a positive t squared minus a 5t plus 4. And if we're trying to evaluate that at 3, we just have e to the negative 3 times 3 squared, which is 9, minus 5 times 3, which is 15, plus 4. And so that just ends up being negative 2e to the negative 3. And if you prefer, you can rewrite that as negative 2 over e cubed. Doesn't really matter. And we want to find all values when the acceleration of the particle is 0 here in part E. So we just need to set a of t, which is e to the negative t times t squared minus 5t plus 4 equal to 0. Well, we know that this is always positive, and this factors to t minus 4 and t minus 1, so that equals 0 when t is 4 and when t is 1. And both of those are in the original domain. They're both positive numbers. Therefore, those are the two places when the acceleration of the particle is 0. All right, here we've got a mean value theorem problem. So we want to figure out if this function satisfies the hypotheses of the mean value theorem on the closed interval from 0 to 1. And so if it does, we want to then find the actual values of c where it's satisfied. So we can note that the domain of this is just x is not equal to 2, right? And so in order to make sure it satisfies the conditions, we need to state that f is continuous on the interval from 0 to 1, right? Which it definitely is, right? Because rational functions are continuous on their domain. And this is definitely on the domain of the function. The domain restriction is just at x equals 2, right? So 0 to 1 doesn't include 2, so it must be continuous. Then we need to find f prime of x just to see if it exists. So we can use the reciprocal rule for that. That's the opposite of the constant times the derivative of what's in the denominator. So that's 3 times 2 minus x squared times the derivative of 2 minus x, all over 2 minus x cubed, and then squared, so 2 minus x to the 6th, which will simplify down into a negative times a negative is going to cancel out. The 12 will stay, but the 2 minus x squared over 2 minus x to the 6th should just become 2 minus x to the 4th. And the only place where this doesn't exist is at x equals 2. So we'll say that this exists on the open interval from 0 to 1, which is what we were looking for. So f is differentiable on 0 to 1. So we've shown that it meets the criteria for the mean value theorem. Then we'll just go right in and find f of 1 minus f of 0 over 1 minus 0. Well, f of 1 is 4 over 1 cubed, so that'll just be 4. And f of 0 is 4 over 2 cubed. 2 cubed is 8, so 4 over 8 is a half. 4 minus a half ought to give us 7 halves. So our average rate of change is 7 halves, and that should equal our derivative, 12 over 2 minus c to the 4th, right? We'll replace that x with a c because we say f prime of c equals that. Then we'll just do some cross multiplication. So we have 7 times 2 minus c to the 4th equals 24. We have 2 minus c to the 4th equals 24 sevenths. And then we end up here, if we take the 4th root, we have 2 minus c equals positive or negative 4th root of 24 sevenths, or c is equal to, we end up with a 2 plus or minus the 4th root of 24 sevenths. Well, we want the one of those that is actually on the interval from 0 to 1. 2 plus a positive number is not going to be between 0 and 1, but 2 minus that number is. So c is going to equal 2 minus the 4th root of 24 sevenths only. We don't want both of them. We only want the one that's on our interval. All right, for our next one here, we want to see if this satisfies the hypotheses of the mean value theorem on the interval 1 to 3. Well, we can immediately see that x cannot equal 2 here, right? We have a vertical asymptote at x equals 2. So f is not continuous on the closed interval 1 to 3. Right? We have an infinite discontinuity. We could write that if we want. Good thing to say there. It's an infinite discontinuity. And therefore, the MVT does not apply. And that's all you have to do for it. Say it's not continuous, or if it's not differentiable, say it's not differentiable. Give a reason, and say the mean value theorem doesn't apply. All right, on our next one here, we're going to try and determine if this function satisfies the hypotheses of the mean value theorem again on the interval -2 to 1. So first we'll look at the domain, right? X can't be 3. Well, that's not a problem, right? So not on the interval -2 to 1. So we'll say f of x is continuous because rational functions, we'll say it's continuous on -2 to 1. Make sure you actually state the interval, right? So f(x) continuous on -2 to 1 because rational functions are continuous on their domains. And they also happen to be differentiable on their domains, but we'll prove it because we need f prime anyway. F prime of x is the denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, which is also just 1, all over the denominator squared. Well, that gives us x minus x, which cancels, and -3 minus -1, which is -2. So we get -2 over x minus 3 squared, which exists on the open interval from -2 to 1. So f is differentiable on -2 to 1, right? The only restriction here is x cannot be 3 again. So what this tells us then is that our derivative, -2 over x minus 3 squared, should equal the average rate of change. So f of 1 minus f of -2 over 1 minus -2. Well, f of 1 is just going to be 0, right? 1 minus 1 is 0, so that's an easy one. F of -2, well, that's -2 minus 1, so that'll be -3. And then over -2 minus 3, which is -5, right? All divided by 1 minus -2, which is 3. So we have -3 over -5. So that's really just -3/5 divided by 3, which should equal -1/5. And we'll set our derivative in terms of c equal to that. And there was our derivative, right? -2 over x minus 3 squared. So -2 over c minus 3 squared. We'll cross multiply and cancel the negatives. So we end up with c minus 3 squared equals 10, right? Or c minus 3 equals plus or minus root 10, or c is 3 plus or minus root 10. Well, we want the one that's on the interval -2 to 1. A positive 3 plus the square root of 10 is more than 6. That's not between -2 and 1. So we only want c equals 3 minus root 10. All right, for our next one here, we're just going to be looking for the horizontal tangent lines of f of x equals x squared minus ln of x. So we'll start off, to find a horizontal tangent line, we just need a derivative, right? F prime of x should be equal to 2x minus 1 over x. And we just want to know, when is that equal to 0? So we'll get a common denominator, right? So we'll have 2x times x, or 2x squared minus 1 over x. When we set that equal to 0, really all we care about is the numerator equaling 0, which will be when x is positive or negative square root of a half, or 1 over root 2. And for that, all we have to do is recognize, first of all, that the negative one is not in the domain, right? Because our domain includes only positive numbers because of the natural log. So only 1 over root 2. And that clearly does not make the denominator here equal to 0 also, so we don't have to worry about that. So we just need to find f of 1 over root 2 to find the equation. Well, that'll be 1 over root 2 squared, which is a half. And then minus the natural log of 1 over root 2, which would be okay. But it might be nicer to look at this. Right, this is the same thing as 1/2 minus the natural log of 2 to the, we'll write it as just, root 2 to the -1. Couldn't do that. And then that -1 can come out in the front. So this becomes 1/2 plus the natural log of root 2. We'll say y equals that. Or we could say y equals 1/2 plus 1/2 the natural log of 2, right? Because we could also pull that square root out as a coefficient in front, right? That square root's a power of 1/2. So either of those are perfectly good answers. I would take either of those. I would have taken this one up here too, but these look a lot nicer and is more likely what you'd see in a multiple choice on the AP test. All right, again, horizontal tangent lines here. So we'll just take the derivative. F prime is just going to be 3x squared minus 3. Never undefined, so we don't have to worry about things that make it 0 also making it undefined. So we'll just set this equal to 0, giving us x is equal to plus or minus 1. That should be pretty easy to solve. Add the 3, divide by 3, square root. So we just want f of 1, and we want f of negative 1. F of 1 is 1 minus 3 plus 1, which is negative 1. And f of negative 1 is negative 1 plus 3 plus 1, which is just 3. So our two equations are y equals negative 1 and y equals 3. All right, again, just looking for the horizontal tangent lines. This time it's an implicitly defined function. So a little bit more of a pain here. So we'll start by just taking our derivative. Derivative of xy is going to be x dy dx plus y. That's with the product rule. And then the derivative of minus x squared y will be minus x squared times the derivative of y. So minus x squared dy dx. And then plus the derivative of negative x squared, which is minus 2x times the y. And then the minus xy squared will be, we'll do the minus x times the derivative of the y squared. So it's minus 2xy dy dx. And then we'll do the derivative of the minus x, which is negative 1, times the y squared. All equals 0, not equal to 3, because remember we have to take the derivative of both sides of this equation. All right, so there is our first step. Step 2 is going to just be to solve for dy dx. So I'm going to factor out the dy dx's on the left-hand side out of everything that has it. So that's x minus x squared minus 2xy. And then on the right-hand side, there's nothing, but I'm going to add all those terms over that don't have a dy dx. So I'm going to get a positive y squared, a positive 2xy, or a positive y squared from this, positive 2xy from that, and a minus y when I bring the positive y over. So my dy dx should equal y squared plus 2xy minus y, all over x minus x squared minus 2xy. Well, we're only concerned about when this thing is equal to 0. So we'll say that it's equal to 0 when y squared plus 2xy minus y equals 0. Or if I factor the y out of this, when y times y plus 2x minus 1 equals 0. So if we look at this, we should be able to see that that gives us y equals 0 as a possibility. And it also gives us y equals 1 minus 2x as a possibility. Right? So y equals 0. The first thing you do is plug it back into the original equation. If I plug into the original equation, I get 0 minus 0 plus 0 equals 3. Well, that's not true. So we can immediately eliminate that. The next thing we'll do is plug the y equals 1 minus 2x back into the original equation. But since I'm looking for horizontal tangent lines, I think it's going to be nicer for us to maybe solve this for x first and plug it back in so everything's in terms of y. I don't have to do a second step there plugging it back in. So if I rearrange this, I can say that x is equal to 1 minus y over 2. And so I'll take that and I will plug that back into my original equation. I'll replace all the x's with 1 minus y over 2. So I think we're going to need a new page to do that. My original equation was xy minus x squared y minus xy squared equals 3. And we're going to do the substitution that x is equal to 1 minus y over 2. So that's going to give us a 1 minus y over 2 times y minus a 1 minus y over 2 squared times y minus a 1 minus y over 2 times y squared is equal to 3. And we can simplify this out. I'm just going to, I think we can multiply everything by 2, right, if we want to. And then I don't have to worry about those denominators. So if I multiply everything by 2, I'm going to get an equal 6 over here. And I'm going to have y minus y squared. And then minus y times 1 minus y squared. Actually, I forgot that one's being squared. So if I multiply by 2 there, that's not actually going to work. Right? What we actually need to do is we need to multiply everything by 4. So this needs a 2. This one, when I multiply by the 4, right, that 2 squared and the 4 will cancel. And of course, this will have to change to a 12. Right, if we're multiplying everything by 4. And so then we'll have a minus 2 times 1 minus y times y squared. And if I distribute all this out, I'll have 2y minus 2y squared. And then minus a y times a 1 minus 2y plus y squared, and then minus 2y squared, and then plus 2y cubed. It's still equal to 12. We can probably combine some more stuff here. Well, we'll do it in a second. We have 2y minus 2y squared minus y plus 2y squared minus y cubed minus 2y squared plus 2y cubed equals 12. And then from there, now we'll combine all of our like terms. So we've got looks like we've got a negative y cubed and a positive 2y cubed. So that'll be a y cubed. So we've got those two taken care of. We've got a 2y squared and a negative 2y squared, which will cancel. And then another negative 2y squared. And then we've got a 2y with a minus y, which will just be a plus y. And then if I bring the 12 over, because we're going to need to do that, we'll say minus 12 equals 0. So now what we want to do here is we want to figure out how to factor this equation. And it doesn't factor by grouping. So we have to use the rational root theorem. The rational root theorem says possible rational roots are the factors of 12. So positive or negative 1, positive or negative 2, 3, 4, and 6. All over factors of the leading coefficient, which is 1. So really, the possible rational roots are 1, 2, 3, 4, and 6, as well as the negative 1, negative 2, negative 3, negative 4, and negative 6. So what we'll do to try and factor this is we'll just use synthetic division with them until we come up with one that actually factors cleanly. So now I've already done the problem. You'd probably start guessing with 1 and then probably with 2 or with negative 1. But I know which one works, so I'm going to just go with the one that works so we don't have a bunch of unneeded work. Remember, the one that works is the one that when you finish synthetic division ends with a 0. If it doesn't end with a 0, you're going to have to keep testing the factors until you find one that works. So I know that 3 should work. So I put my 3 up here, and since it was y cubed, it's 1y cubed. And then it was a minus 2y squared, so minus 2. And then it was plus 1y, and then minus 12. So those are my coefficients going across. So bring down the 1, multiply it by the 3, add the 2 together. Negative 2 plus 3 is 1. And then multiply by the 3. 1 and the 3 added together is 4. Multiply by the 12 is 12, and you get 0. So we know that the factor was y minus 3 and y squared plus y plus 4. And that's what we want to set equal to 0. Okay? And so this gives us y equals 3. And then this one, just like we did with the previous problem, b squared minus 4 times a times c is negative, which means this has no real solutions. Which means that the only possibility that we have here for a horizontal tangent line is at y equals 3. Right? We should always go back and just check that if I plug y equals 3 into the original equation, we actually get values for x. So we had xy, so that'd be 3x if y is 3. And we have minus x squared y, so that'll be minus 3x squared. And then we had minus xy squared, which would be minus 9x, is equal to 3. And so if I bring all that to one side, we have 3x squared on the right-hand side now, and then plus a 6x, and then plus a 3 is equal to 0. And we can see that does have solutions, right? If we factor out the 3, it's x squared plus 2x plus 1 equals 0, or 3 times x plus 1 squared. So it looks like, yeah, there's a horizontal tangent line of y equals 3, and it's at the place where x is equal to negative 1. Now, you don't need to find the actual value there, but you just need to show that there actually is one. And for this next one, we're now looking to determine the equations of the vertical tangent lines. And so we still need to find a derivative, but this time, instead of seeing when it's equal to 0, we're going to see when it is undefined. Right? So we'll start off here just by, like I said, taking the derivative. So the derivative of 2x times x minus 1 to the 1/3, we'll have to find that using the product rule. So f prime of x is just going to be 2x times the derivative of x minus 1 to the 1/3, which is 1/3 of x minus 1 to the negative 2/3 times the derivative of x minus 1, which is just 1, and then plus the derivative of 2x times the x minus 1 to the 1/3. Now we'll factor out the x minus 1 to the negative 2/3 from all of that. Right, so if we do that, we've got 2x over 3. We'll write out our x minus 1 to the negative 2/3 first, times 2x over 3, and then plus 2 times x minus 1 to the first power, right? Because negative 2/3 times x minus 1 to the negative 2/3 times x minus 1 to the first is just x minus 1 to the 1/3. So we end up with this, which is we'll put that x minus 1 to the 2/3 in the denominator now, and we have 2x over 3. So if I want to get a common denominator here so that I can drop that 3 to the denominator also, we'll have 2x plus the 6 times x minus 1, which is just going to be 8x in our numerator minus 6. Right, so we end up with 8x minus 6 over 3 times x minus 1 to the 2/3. Right, and so what we want to do is set this to be undefined. Right, so it's undefined if the denominator, the x minus 1 to the 2/3, is equal to 0, which would be at x equals 1. So it's possible that we have a vertical tangent line here at x equals 1. Now, we just need to make sure then that there is actually a value of our function, that f of 1 actually exists. Right, so f of 1 is equal to 2 times 0. Right, so that tells us that we definitely have a point there, and that we must have a vertical tangent line of x is equal to 1. And actually, one thing to add to this is we want to make sure that our derivative doesn't change signs there, because when we have a like if our derivative changes signs at a place where the derivative is undefined, then that's a corner or a cusp normally, or a discontinuity of the original function. We have to make sure this is actually a vertical tangent line, right? And so the values that I put on my sign chart would be 1, and then I'd also want to put on the value that makes the numerator 0, which is 3/4. So if I put on 3/4 and 1, you can see if I put in something between 3/4 and 1 into my derivative, let's say that's like 7/8. If I put in 7/8, then I end up with a positive in the denominator and a positive in the numerator. So we're increasing here. And then after 1, if I put in something like 1,000, we're still going to be positive here, which tells us that the function doesn't have a corner or a cusp there. So we want to check that as well. So we're checking to make sure the function's not undefined and to make sure that there's no corner or cusp from our sign chart. And then for this one, we're going to do the same thing. We're just looking for the vertical tangent line. So I'm going to rewrite this as 3 minus x to the 1/3 times x minus 2 to the 1/3, just because I think it makes it easier for us to look at to take the derivative here. So our derivative f prime of x, we'll have to use the product rule. So it should be the first function, 3 minus x to the 1/3, times the derivative of the second, which is 1/3 of x minus 2 to the negative 2/3, times the derivative of x minus 2. And then plus the x minus 2 to the 1/3 times the derivative of 3 minus x to the 1/3, which is 1/3 of 3 minus x to the negative 2/3 times the derivative of 3 minus x, which this time is negative 1. And so now we're going to have to take this and simplify it down as best we can. So I'm going to rewrite each of these sort of in their fractional form so we can take a look at them and get a common denominator. So the first one here is going to be 3 minus x to the 1/3 over 3 times x minus 2 to the 2/3. And then we're going to have a plus. Over here, we're going to have a, actually it's going to be a negative because of that negative 1. So we'll throw a negative sign in the middle right now, right off the bat here. So we have a minus here. And then we've got the x minus 2 to the 1/3 in the numerator. And then we've got a 3 and a 3 minus x to the 2/3 in the denominator. Now, if we want to get a common denominator to put this all together, we're going to have to multiply this one by 3 minus x to the 2/3, which means we'll multiply the top by 3 minus x to the 2/3. And this one will need an x minus 2 to the 2/3, which means we'll multiply the top by x minus 2 to the 2/3, which works out really nicely because now that just gives us 3 minus x minus 2 all over 3 times x minus 2 to the 2/3 times 3 minus x to the 2/3, which simplifies down into, let's see, we end up with a 5 minus 2x in the numerator all over 3 times x minus 2 to the 2/3 times 3 minus x to the 2/3. And so we can see that this is undefined if x is equal to 2 and if x is equal to 3, which are our possible vertical tangent lines here. And we can see that it equals 0 if x is 2/5. So we're going to make that sign chart like we did with the last one. Just, sorry, not 2/5, 5/2. Yikes, that was almost really bad. Right, so x equals 5/2 then. Right, and so that's when it's equal to 0. And so we'll make our sign chart using 2 and 5/2 and 3 here. Right? So if I put on 2 and 5/2 and 3, if I put in something more than 3, like a billion into this, well, I know the denominator is always positive, and 5 minus 2 times a billion is definitely negative. If I put in something between 5/2 and 3, so like 2.75, the denominator is still positive, but 5 minus 2 times 2.75 is negative. And so if I put in something like between 2 and 2.5, like 2 1/4, then the numerator is going to be positive, and something like 0 is also going to make that numerator positive. So we can see that at x equals 2 and at x equals 3, we don't have a sign change of our derivative, right? We're increasing all the way, then decreasing all the way, which means that our function doesn't have a corner or a cusp there, and our original function doesn't have any discontinuities, right? Because you take the cube root of anything. So we do have two vertical tangent lines of x equals 2 and x equals 3. All right, for this one, it's an implicitly defined function here. So we'll take the derivative using implicit differentiation, right? So that'll give us 2x minus 2x times the derivative of y. and then plus the derivative of negative 2x, which is negative 2 times y, minus 2y dy dx is all equal to 0 and not 4, because we have to take the derivative of both sides. So we will then solve for dy dx. I'll just leave the 2x minus 2y on the left side and add the other terms to the right-hand side. So that's going to give me a 2x dy dx plus a 2y dy dx on this side. We can divide everything by 2, and I can also factor out the dy dx here. So we have x minus y equals dy dx times x plus y, or dy dx should be equal to x minus y over x plus y. And of course, if you got y minus x over negative x minus y, that's fine too. It doesn't really matter. So we want to find out when this is undefined, right? This is undefined if x is equal to negative y. And it's equal to 0 if x is equal to y, which we just need to make sure that whatever values we get here don't also satisfy that. Well, x equals negative y and x equals y. The only things that satisfy that would be when x or y is equal to 0, right? So, we won't have to worry about that, because if we get 0 for x and for y, we can see that that doesn't actually work in the original equation. So now what we'll do is we'll just go back to our original equation. We're going to replace all the, in fact, what we'll do is we'll rewrite this as y equals negative x, so that all of our values are in terms of x in our original function. So when I plug this into my original, right, I'll get x squared minus 2x times negative x, and then minus the negative x squared. So minus x squared is equal to 4. And so all we need to do then is just solve that for x. And so we've got x squared and a minus x squared, which will cancel, and then a negative 2x times a negative x is a 2x squared equals 4, or x squared equals 2, or x equals positive or negative root 2. And of course, neither of those are going to satisfy x equals y, right? Because, well, if it satisfies y equals negative x, right, it's not going to satisfy y equals x also. We should check and make sure that those actually yield solutions in our original function. So we'll do that over here. And if I plug positive or negative root 2 into that, I'm going to get just 2 for x squared. So I have 2. And then I end up with minus 2 times root 2 times y. So minus 2 root 2y minus y squared equals 4. That'd be if I put in positive root 2. And so a positive y squared, if I bring that over, plus a 2 root 2y minus, plus a 2. And I think, we can, if we try and plug that in, or if we try and solve that quadratic, we can just see that using the discriminant, we get b squared, right, which is 2 root 2 squared, which is 8, minus 4 times a times c, right, should equal 0, right, which tells us this does have one real solution. So x equals root 2 works. And then if we do x equals negative root 2 squared is still just a 2. And then plus 2 root 2 times y now as we plug that into the original, minus our y squared is still equal to 4. Getting that all to one side gives us a positive y squared minus a 2 root 2 times y plus 2 is equal to 0. And our discriminant there is the same thing. It's 8 minus 4 times 1 times 2, which equals 0, telling us again this has one real solution, which means that x equals negative root 2 is also going to be a vertical tangent line here. All right, so for our next one, we want to find the value of the x value of the point on the graph of x to the 3 halves minus 4 that's closest to the point 1, negative 4. And so to do that, we need to write out a function that represents the distance between the point 1, negative 4 and any point on the function x to the 3/2 minus 4. So that'd be a point x, comma, x to the 3/2 minus 4. So the distance then should be, we'll call it d. D is equal to the square root of the first x value, x, minus our other x value of 1 squared, plus x to the 3/2 minus 4 minus negative 4 squared. Or in other words, it should be the square root of x squared minus 2x plus 1 plus x to the 3/2 squared, which is just x to the 3rd. Okay? And so we can take the derivative of this, right? D prime should just be 1 over 2 root x cubed plus x squared minus 2x plus 1 times the derivative of that, which is 3x squared plus 2x minus 2, if we just go ahead and rewrite that in a descending power order. And so then we just need to see when this is equal to 0. We don't really need to worry about its undefined when it's undefined, because we know that the point 1, negative 4 is not on the graph, right? And so the distance, which is the same as our denominator here, just times 2, is never equal to 0. So really, we just want to know when is 3x squared plus 2x minus 2 equal to 0. And we'll just use the quadratic formula on that, right? It's the opposite of b plus or minus the square root of b squared. Right? So the square root of b squared, 4, minus 4 times 3 times negative 2, all over 2 times 3. Right? Well, that's going to give us negative 2 plus or minus the square root of, let's see, it's 4 plus 24, so that'd be 28 over 6, which is negative 2 plus or minus 2 root 7 over 6, or negative 1 plus or minus root 7 all over 3. And so, of course, we want the one that is going to actually make sense for our problem. So we can either find a second derivative or we can do a sign chart here. So I think we'll just do a sign chart here to see which one. Well, actually, we don't even need to worry about that, because negative 1 minus root 7 over 3, that one's not even in the domain. So our only possibility is negative 1 plus root 7 over 3, right? Negative 1 minus root 7 over 3, that's a negative number. And a negative number, we can't square root. So that's not in the domain of our original function. So we'll just make sure that if I put in something more than that, like a billion, right, into our derivative, we get a positive, right? And then if I put in something, less than that, right, negative 1 plus root 7 over 3, like if I just say like negative 0.1, if I plug in negative 0.1, my denominator is always positive, but if I plug in negative 0.1, that's, I think, pretty clearly going to be a negative number there, right? Because negative 0.1 squared times 3 is very small positive, and it's definitely less than 2, and I'm going to be subtracting more than 2, so we get a negative here, which tells us our function decreases then increases. So the x value of negative 1 plus root 7 over 3 is the location at which we are closest to the point 1, negative 4 on the graph of x to the 3/2 minus 4. All right, and for our next one here, we're just going to look at sand falling into a conical pile where the radius is always 6 times the height. So the radius is 6h. So we'll make a note of that. The sand is falling at a rate of 22 cubic inches per second. That's a dV dt value. So dV dt is going to be 22, right? And we want to know at what rate is the radius changing. So that's dr dt when the radius is 10. So we want to do this problem using a volume of a cone, right? Volume is 1/3 pi r squared h, but we want to do it all in terms of r, right? Because we're given r and we are looking for dr dt. So we'll replace the h in our problem with r over 6, right? Because that's what h is equal to. So we'll have volume equals 1/3 pi r squared times r over 6. which is 1/18 pi r cubed. And so we said 1/18, we should probably write 1/18. So 1/18 pi r cubed. When we take our derivative with respect to time, we'll get dv dt is equal to 3/18 or 1/6 pi r squared dr dt. And now we just want to solve for dr dt. So dv dt was 22. And then we have pi over 6 and our radius of 10 squared times dr dt. And so now we'll just simplify all of this down. Right? We end up with, looks like we end up with 22 times 6, right? 22 times 6 is 132. So 132 over 100 pi is our dr dt, which those both divide by 4. So 4 times 33 should be 132. So this is 33 over 25 pi, and we're in inches per second here. All right, and for our next one here, we've again got sand falling into a conical pile. This time the radius is 1/2 the height. The sand is falling at a rate of 36 cubic inches per second. So that'll be dv dt is 36. We want to know at what rate is the height of the pile changing. So what is dh dt when the radius is 6? Well, this time, since we're looking for dh dt, we're going to want to put everything in terms of h for our volume equation. Right, so volume is 1/3 pi r squared h, but we want it in terms of h. So we'll just replace the r with 1/2 h. So volume is 1/3 pi times 1/2 h squared times h. So volume is 1/12 pi h cubed. Okay? And we'll then take our derivative, dv dt, should be 3/12 or 1/4 pi h squared dh dt. And we'll plug everything in. Well, 36 is our dv dt. We have pi over 4, but we don't have h. But we do have r, right? So r is 6. So 6 is 1/2 the height. So the height ought to be 12. So we have 12 squared times dh dt. And from there, we should be able to solve for dh dt. Right? dh dt should just equal, well, 4 times 36 is 144. And then we'll divide by 12 squared times pi, which is 144 pi. So we just get 1 over pi, and we're talking in inches per second again. So for this problem, we have a 13-foot metal pole that's leaning against a wall that meets the ground at a right angle. So here's our right angle. Here's our 13-foot long pole. That pole is sliding down the wall, and we're looking at the instant when the top of the pole is 10 feet above the ground. That'd be our y value. And then we've got an x value here for the distance that the bottom of the pole is from the angle there. And so we want to know the rate of change of the base of the pole as it slides away from the wall. So we're looking for dx dt. We do have dy dt, although we have to be careful with it, right? It says that the pole is sliding down the wall at 3 feet per second. Well, since the length of y is getting smaller, that rate of change needs to be negative. So we're going to get -3 for dy dt. And then we are interested in this happening when y is equal to 10. And so the equation that we're going to write here to solve this is just going to be Pythagorean theorem. It's just going to be x squared plus y squared equals 169. Right? And when we take the derivative, we'll just get 2x dx dt plus 2y dy dt is equal to 0. Right? And then we solve that for dx dt, which is what we're looking for. Right? dx dt, the 2's will cancel, right? So dx dt will just be negative y dy dt over x. Right? And so we need to plug in the y and the dy dt, which apparently I wrote dy dx, even though I said dy dt, so dy dt, and we need to plug in an x value. Well, we don't have an x value, so we need to figure out what that x value is by just using the Pythagorean theorem. X squared plus y squared, which is 100, is 169, so x squared is, subtract the 100, you'll get root 69. The square root of 69 is 3 times 23, right? Root 3 times root 23, those don't simplify, so we'll just leave, we wrote x squared is 69, so x is root 69, right? That does not simplify. So now we'll just plug everything in. We've got negative y, which is negative 10, times dy dt, which is negative 3 over root 69, which is just 30 over root 69, and our units were feet per second here. So that's our answer to the first part of this question. For the second part of the question, we're asked to find the rate of change of the area of that triangle. Well, the area of that triangle is just 1/2 of x times y. So the rate of change of it, dA dt, should just be 1/2 of the derivative of xy, which will be x times the derivative of y with respect to t, plus y times the derivative of x with respect to t, because we're using the product rule there. So now we just use all of the values that we had from the previous problem. X was the square root of 69, and then dy dt was negative 3, and then y was 10, and dx dt was 30 over the square root of 69. And so we'll simplify this down a bit, hopefully. So we'll just want to get ourselves a common denominator here. So we'll multiply by the square root of 69 and the square root of 69, which is like squaring that. So it looks like we end up with our 1/2 still out in front, and then 69 times 69, or square root of 69 times square root of 69 is just 69. If we multiply that by negative 3, let's see, that's negative 207. And then we're going to add to that 300 over root 69. And negative 207 plus 300 should be 93. So we end up with our final answer of 93 over 2 root 69 feet squared per second. Here we have the same situation going on, except now we're asked for the rate of change of the angle made by the ground and the pole. So we still have this same 13, and we still have y, and we still have x, but we want the rate of change of the angle made by the ground and the pole. So we'll call that theta. And we can use either y or x for this. It doesn't really matter. I'll just use sine of theta, right? So we'll do sine of theta is equal to y over 13, right? Opposite side over hypotenuse. Or 13 sine theta is equal to y. When I take the derivative of both sides, we have 13 cosine theta d theta dt is equal to dy dt. And you don't have to bring the 13 over. In fact, we're going to divide it over in a second again. But I found that people often have trouble for some reason taking the derivative of y over 13, which would just be 1/13 dy dt. But if we bring it over to the other side, people don't seem to have any issue with it. So we'll leave it there. So now we're going to do 13 times the cosine of theta. Well, the cosine of theta is adjacent over hypotenuse. That's x over 13. And our x value that we had previously in the problem, right, was the square root of 69. So it's the square root of 69 over 13. Right? And then times the d theta dt. And actually, we won't have to bring that 13 over. We can see now that we just end up with those 13s canceling. And our dy dt that we had before was negative 3. So we end up with d theta dt is equal to, well, the 13s cancel, so it's just negative 3 over root 69, and these are radians. per second. And if we want to find the rate of change of the other angle, right? This is the angle made by the wall in the pole. We'll call that one theta now. And again, doesn't really matter which trig function we use. I'm just going to use sine again. The sine of this theta, we'll call this one theta, now is equal to the opposite, which is x over 13, or 13 sine theta is equal to x. When we take the derivative, we just get 13 cosine theta d theta dt is equal to dx dt. And of course, we're solving for the d theta dt here. So, but we'll plug everything in. Cosine of theta is now y over 13. Well, our y value before was 10, so this is 10/13 d theta dt is equal to dx dt, and our dx dt before was 30 over the square root of 69. We got that in part A, we found that. And so now these 13s will just cancel. And when we divide by 10, we get d theta dt is now just 30 over 10, which is 3 over root 69 radians per second, right? So those angles are changing at the same rate, just one's getting bigger and one's getting smaller. All right, for our next one here, we've got a 25-foot long ladder that's leaning against a wall. So basically the same idea as the last problem. And so I've got this right angle. We've got a 25-foot ladder. We've got an x distance and a y distance, and we want the rate of change of the base of the ladder. So we're looking for dx dt, right? That's what we want to find. The bottom of the ladder, we're talking about it being 7 feet away, so that's an x is 7. And the pole is sliding down, or I guess it's a ladder. I wrote pole just like the last problem, but it should be a ladder. The ladder is sliding down the wall, so dy dt is -5 because that y value is changing. And so we'll just do the exact same thing as before. We'll just do x squared plus y squared equals 25 squared. And when we take our derivative, we get 2x dx dt plus 2y dy dt is equal to 0. The 2's will cancel. We divide both sides by 2. And we're looking for dx dt, so dx dt should just be negative y dy dt over x. Well, in order to plug all those in, we need the value of y, right? So we should know, with any luck, we should know that this is a Pythagorean triple. But if we don't know that it's a Pythagorean triple, right, we can just plug it in. Right, we get 7 squared, so 49 plus y squared is equal to 625, or y squared is equal to 576, which tells us that y is 24. So dx dt ought to be -24 times dy dt, which was -5, all divided by our x value, which was 7. So we end up with a positive 120 over 7 feet per second. And with the last one, we did the same thing, right? We found the area, the rate of change of the area, which is 1/2 xy. So dA dt should just be that 1/2 times x dy dt plus y dx dt. And we now have all of those values. So it's 1/2 of our x, well, x was 7. dy dt was -5. And then y was 24. And then our dx dt was 120 over 7. And so we end up there with -35 plus whatever that ends up being. Let's see, that's 1/2 of -35 plus what is that going to be here in terms of sevenths? right? We got to multiply out 24 times 120. That should be 2,880 over 7. And negative 35, if we turn that into sevenths, let's see, that should be negative 245 sevenths. And so if we add the negative 245 plus the 2,880, that should be 2,635 over 7. And then with the 2, that should be 2,635 over 14. And our units here are feet squared per second. So kind of annoying arithmetic there, but otherwise just the same as the last problem was. Right here, we want to find the rate of change of the angle made by the ground and the ladder. So we'll call that theta here. And then, well, we can just do what we did before, right? The sine of theta is equal to y over 25, or 25 sine theta is equal to y. When we take the derivative, that gives us 25 cosine theta d theta dt, because we're doing it with respect to t, is just equal to dy dt. And the cosine of theta, well, we should have that, right? The cosine of theta should just be the x value over 25, and our x value within this problem, I believe, was 7, right? The bottom ladder is 7 feet away, so 7 over 25. And then we have our d theta dt is equal to our dy dt, and our dy dt was negative 5, right? We're sliding down at 5 feet per second. The 25s will just cancel, and we end up with d theta dt is negative 5/7 radians per second. And for part D, we are just asked to find the rate of change of the other angle. Probably should have used a different variable, either theta 1 and theta 2, or we use alpha this time. And we've still got 25, we've still got our x, and we've still got our y down here. So the sine of alpha is just equal to x over 25, or 25 times the sine of alpha is equal to x. So we can take the derivative to get 25 cosine of alpha d alpha dt is equal to dx dt. Then we just plug it in. 25 times the cosine of alpha, well, the cosine is y over 25, and our y was 24. We found that in part A, right? So 24/25. And then d alpha dt is equal to our dx dt, which was dx dt was our answer from part A, which was 120 over 7. So this gives us d alpha dt is, well, we've got the 25s that cancel. So it's 120 over whatever 7 times 24 is. But we should be able to simplify that down, right? 120 over 24 is just 5. So this is 5/7 of a radian per second. All right, for our next one here, we've got water flowing into a conical tank oriented with the vertex down. So I'm going to draw that. There's my conical tank. Vertex is down, right? Conical, right? Just means shaped like a cone. So our vertex is down. We have the water's flowing in at a rate of 5 cubic feet per minute. So that's a rate of change of the volume. dV dt is 5. And we know that the height of the tank, which the height of the tank is not changing, right? The height of the tank itself is just 12. And the radius of the tank is 3. We want to find the rate of change of the height of the water in the tank when the height of the water is 7 feet. So we're looking for dH dt when h is 7. Well, as this thing fills up, right, we end up with a new smaller cone of water inside where the height and the radius of that are changing. Well, conveniently, we can treat these like similar triangles, because that's exactly what they are. Right? They share that base angle there, right down here. Right? They share this angle that I've marked. And then they both have a right angle. So the ratio 3 for the radius to 12 for the height of the big cone should be the same as the radius to the height of the smaller cone. And so since we've got everything in terms of h, we want to turn our volume equation, which is 1/3 pi r squared h, all into terms of h. So we want to solve this for r in terms of h. Well, 3/12 is just 1/4, so if I multiply by h, we get r is h over 4. So our volume should become 1/3 of pi times h over 4 squared times h. And so that ends up giving us our volume is equal to 1/48 pi h cubed, or dv dt is, if we take that derivative using the power rule, 3/48, which I'm not going to write that. 3/48 simplifies down to 1/16, right? So 1/16 pi h squared dh dt. Our dv dt is 5. We've got our pi over our 16. Our h value was 7, so 7 squared. And then dh dt. And we're just solving for dh dt. So dh dt should be, well, we'll do the 5 times the 16. 5 times 16 is 80. So it's 80 divided by 7 squared times pi, which is 49 pi. And these are in feet per, what do we have? Feet per minute. All right, for our next one, same basic problem type. The water is still flowing into this conical tank where the vertex is oriented down. It's flowing in, or sorry, it's flowing out this time. So our dv dt value is going to be negative, right? It's draining out of this tank. So dv dt is going to be negative 3 cubic feet per minute. And we know that the height of the tank, which is not changing, the height of the tank, the full tank, is 12. And the radius, oh, sorry, it's not 12, it's 18. Should probably read those numbers, right? The height of the tank is 18. And the radius is 9. And as the water flows out of the tank, the water level is going down, right? And we have a height of the smaller cone of water with a radius. And that ratio, since those are, again, similar triangles, right? They both have a right angle, and they both share this angle at the bottom, right? That means that 9 over 18 should be the same ratio as r over h. And again, we're looking for the rate of change of the height of the water. So we want dh dt when the height is 12. So we're going to put everything in our volume equation for a cone. We're going to put it all into terms of h so we can deal with it that way. So we need to know what r is. Well, r is equal to h over 2, or 1/2 h, right? Because 9/18 is a half, and multiply by the h. So we have volume equals 1/3 pi times h over 2 squared times h, or the volume is pi h cubed over 12, giving us, when we take the derivative with respect to t, dv dt equals 3/12, or 1/4 pi h squared dh dt. Now we can plug in everything that we've got here to just figure out what our value for dh dt is. dv dt was -3. We've got pi over 4. Our height was 12, so 12 squared dh dt, giving us dh dt is equal to, well, let's see, we've got -3. We're going to have to multiply that by 4, which is -12. And then we're going to divide by 12 squared. So -12 over 144 is just going to be -1/12. And then that pi gets divided down also. So -1 over 12 pi. And again, this is feet per minute. For the rest of the problems on this assignment, we're going to be allowed to use a graphing calculator. And we'll remember that we're always going to round our final answer never before our final answer. We're going to round our final answer to 3 decimals or more than 3 decimals. So for this first one, we want to know the x value of the point on the graph of x cubed minus 3x squared plus 1 that is closest to the point 2, 1. So we're looking at a distance between a point on this function, which would be the point x, comma, x cubed minus 3x squared plus 1, right, and the point 2, comma, 1. So the distance formula says that should be the square root of x minus 2 squared plus x cubed minus 3x squared plus 1 minus 1 squared, which is just a distance of the square root of x squared minus 4x plus 4 for the x minus 2 squared. And then, of course, we can see that the plus 1 and the minus 1 are going to cancel out there. And that's going to give us x cubed times x cubed, which will be x to the 6th, and then minus 6x to the 5th plus 9x to the 4th. And of course, that's all inside the now multicolored square root that we have there. So that's our distance, right? And we want to figure out when does the derivative of that equal 0. So we'll take the derivative of it. And as I do that, I'm just going to kind of rewrite this slightly. I'm going to write 2 times the square root of x to the 6th minus 6x to the 5th plus 9x to the 4th plus x squared minus 4x plus 4. And just put those in descending power order. And then times the derivative of that numerator, which is 6x to the 5th minus 30x to the 4th plus 36x to the 3rd plus 2x minus 4. And we could simplify out the numerator there by dividing everything by 2 if we want to, but since we're just putting this into our calculator, I don't think we really need to worry about doing that. So let's just go to our graphing calculator. We'll hit y equals, and if your calculator has the nice little fraction where you hit alpha and then the x value, do that. If not, make sure that you put the numerator into parentheses and the denominator into parentheses. So we'll do 6x to the 5th in our numerator minus 30x to the 4th, and then plus 36x cubed plus 2x minus 4, all divided by 2 times the square root of our original function there, or the original square root that we had, which was x to the 6th minus 6x to the 5th plus 9x to the 4th plus x squared minus 4x plus 4. And then we'll graph this. And we end up getting a function that looks something like this. We want to find when it is at a, when this is at a minimum, not when this is at a minimum, but when this equals 0. And so we can be pretty certain that, you know, any place where we would positive, that any place where the derivative, which is what we just graphed, goes from positive to negative is going to be a maximum. But we'll still find the values, all 3 of the values anyway. So second, and then calculate, and we want option 2 for 0. And to the left, we're to the left of our x-intercept already, so I'll hit enter. And then I'll just go till I'm to the right of my x-intercept, and I'll hit enter again. When it says guess, I'll hit enter a 3rd time, and we'll get 0.5116704. So this is equal to 0 when x is 0.561. No, it was 5. What was it? Probably remember these numbers. It was 5116704. The next one here, we'll go back to our graphing calculator. We'll do second calculate option 2, which is 0. And we'll look for the second one. So we'll move to the left, to the right till we're close to the x-intercept we want. Hit enter. Go to the right of the x-intercept we want. Hit enter again. Now, and that one comes out to be 2. So that's going to be an easy one. Remember, we got x equals 2. And then for our last one, we'll do the same thing. Second and trace, or second calculate, which is option 2 there, 0. we'll go to the right until we are to the left of that x-intercept, and then go to the right of it. We'll hit enter each time, and then we get 2.9874987. And I don't really need to go through all of the annoying arithmetic to plug in these values, and I'm just going to kind of abbreviate these here so that I don't have to write the whole number out, since these aren't going to go into my final answer. This is a sign chart for my derivative. So it's not, I guess it's not f prime, it's d prime. So we'll put that. And if we look at our derivative, well, this is the derivative. The derivative was negative all along here till this first x-intercept. Then the derivative was positive. Then the derivative was negative. Then the derivative was positive. Right? It switched at each of them. So it started off negative, went to positive, then to negative, then to positive. So we've got the distance decreases, then increases, then decreases, then increases. So what we need to do then is we just need to figure out which of those two places where we have a local minimum is actually the smallest. So we need to evaluate the distance at 0.5116704, and we need to evaluate the distance at 2.9874987 and see which one is smaller. And so I'm not going to go through just the typing each of those into our graphing calculator. We're just plugging them into our original distance function. Right? And so if I do that, this first one at 0.511 gives me 1.624662. And the other one gives me 0.9937821. So clearly 0.99 is less than 1.62. So the distance is at a minimum when x is 2.9874987. And of course, if you wish, you can round that to 3 decimals, but you don't need to. All right, our next one here, we're just looking at a motion problem. We saw one of these earlier in this assignment, but this time we're going to be able to use a calculator for it. So we want to find the velocity of the particle at t equals 1, given its position is that function y of t. Well, it's really easy to find the velocity of a particle at t equals 1 if we have the position function given a calculator. Right? We'll just say y prime of 1 is equal to v of 1. Right? And so then we can just put that into our calculator. Right? We can just take our derivative of that function at 1. So if you write this, and then you go into your calculator, and I'm going to, just in case we do need to graph it, I'm going to graph this function, which was the natural log of, it was t squared, but we'll use x squared, right? Natural log of x squared plus 1 minus x, and then plus the sine of x, just so I have it in there, just in case I need it. Right? And then what we'll do is we'll just take the derivative of this at 1. So we'll do secant, trace, and then it's option number 6 down here, dy dx. When you hit that, it doesn't look like it does anything, but if you type in a 1 and hit enter, it will tell you down here that your derivative is 0.5403023. .5403023. And that's our answer. And we also want to be able to find the velocity of the particle at t equals 4. So again, that'd be y prime of 4 is v of 4. So we'll just do the same thing. Although this time, just to reinforce that there's other ways to do this, we can always go back and note first that we've plugged this function in as y1. If we go back to our original screen here at just our blank screen, we can hit math and go down to option number 8 in deriv, which will bring up a derivative. We want the derivative with respect to x of that function that we had placed as y1. So you hit the VARS button just next to clear. And then you go to the second VARS column, y variables. It stands for variables. And then we want option 1, which is function. And we have that function typed in as y1, so we'll just put in y1. And we want the derivative at x equals 4, which comes out to be negative 1.18305538. And part C asks us to find the speed. Well, speed is just the absolute value of the velocity, so that will just be 1.183055538, right? We just want the positive version of that velocity. All right, for part D of this one, it says find the velocity of the particle the first time it's at the origin. So now this is why it was good that we actually graphed this. So we've graphed the function, the position function, and we want to know when it's first at the origin. So we just need to see when that function equals 0. So we'll go back to our graphing calculator, and we'll go back to the graph that we already had, and we'll look for when this function is equal to 0. And so we're going to note that it looks like it's crossing somewhere near the origin. So let's hit zoom and do option 2, zoom in. And then let's kind of zoom in, kind of in between where it looks like we got the two x-intercepts. And it sure looks like that the function there is probably always positive after 0, but it's kind of hard to tell. So if we look at our table here, we can hit second and then graph, which gives us a table. We can see that all the values we see after x equals 0 are certainly positive values, but we may not know exactly like what's going on there right around that point. So we just got to kind of be careful, and we recognize though that like anything that we put into there, we're going to be taking the natural log. If we look back at our function, right? Anything that's close to 0, right? The sign of 0 is positive, and we're going to be taking the natural log of something that is more than 1. So that's going to be something that's more than 0 also, right? Because the natural log of 1 is 0. We're going to be subtracting that t value. So it seems like the values that we're going to get there, since we're going to be taking a couple of positive things and adding them together, and the sine function, right, it increases more quickly than a linear function does right off the bat. So like this value is going to be more than this value, plus we're adding more positive to it. So those values around 0, we don't really need to worry about being below the x-axis there. So our first x-intercept of this, our first place when the position is equal to 0, right, the first time that x of t is equal to 0, is going to be the root. So we're going to do second trace 0. That's over here a little after 2. So we'll hit enter here. We'll go a little beyond it. We'll hit enter. We'll hit enter again. And we'll get 2.56979983. So we'll say that y of t is equal to 0 at 2.56979983. And we want the velocity of the particle there, so that's y prime of, I'm just going to call this a, so I don't have to rewrite it. That'll be the velocity at a. And using our graphing calculator, since we're already on the graph, we'll just say second trace, option 6 for dy dx. And we'll type in that number, which was 2.56979983. And we end up getting dy dx is negative 1.165012. And that is our velocity at that time. So now this question asks us what's the acceleration of the particle the first time it's at the origin, which means we need to do one of two things. We either need to just take the derivative of our velocity function and then evaluate it at, or evaluate its derivative at this same value, right? So take the velocity function, which we'd have to find by taking the derivative of the position function. Or we can use this cool little trick that our graphing calculator will do to find the value. So I'm going to show both ways. So one way is to actually find y prime of t. That'd be v of t, right? Well, the derivative of natural log of t squared plus 1 is 1 over t squared plus 1 times 2t. And then minus 1 plus cosine t. And then we'd want to evaluate that at t equals a. The other option, though, and I'm just going to say this is equal to whatever, well, we're going to get the same value both ways. So we could do that. Or the other option is, if we go into here and we go back to our main screen, we can say we want the math, option 8, the derivative, with respect to x. And then we'll do it again. Math, option 8, with respect to x again, of our function, which was our position function, which we can go VARS, and then y VARS, option 1, option 1. Right, so there's our function. And for the first one, we need to say we want the derivative with respect to x at x. And then for the second one, where we're taking that second derivative, that's when we want to type in that number, which was 2.5697,979,883. And that will give us negative 0.7349. And if you found your velocity function here and you typed that into your graphing calculator and had it evaluate the derivative of that at that same value, you'd end up getting negative 0.7349 as well. And so that is our answer here. Okay, our next one, we're using Newton's method to approximate this root here, the root of x to the 5th minus 3x squared plus x plus 2 on the interval negative 1 to 0. So since I've already given you an interval, you can just kind of make a starting guess. I'm just going to say x naught is equal to negative 0.5, since that's right between negative 1 and 0. We'll find y prime, which is 5x to the 4th minus 6x plus 1. And remember that the formula is x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So that'll be x sub n to the 5th minus 3x sub n squared plus x sub n plus 2, all divided by the derivative, which was 5x sub n to the 4th minus 6x sub n plus 1. And we'll just type in all of this into our graphing calculator, except that we always want to start by typing our first guess and hitting enter, so that we can use the answer button for every x sub n, which is second and then the negative sign. So answer, or x sub n, minus, use the fraction bar if you can, alpha, and the x button next to it. But if that doesn't work on your graphing calculator, just make sure you put the entire fraction in its own parentheses, plus the numerator and the denominator separately into their own parentheses as well. So in the numerator, we have x sub n to the 5th minus 3 x sub n squared plus x sub n plus 2. And it's all divided by 5 x sub n to the 4th minus 6 x sub n plus 1. And when we hit enter, that gives us our first guess there, which is 0.6 repeating, or negative 0.6 repeating. So we'll write that down. X sub 1 is negative 0.6 repeating. And then x sub 2 will be this value. So we'll write that down. And for the next problem, I'm probably not going to write them all down, but on the test, you need to write down all of your little intermediary values here. But just for the interest of saving some time on the video, we won't do that. There's our x sub 3. And remember, what it's doing each time is it's just reevaluating this expression with our new output that we got. So this next one here is negative 0.64417,81941, and x sub 5 then ends up being exactly the same, which means we know we can stop there. And we know that this is a good approximation for that root. All right, this is another Newton's method one. Once again, I've given you the interval. So I'm just going to start off with my first guess being x naught equals negative 0.5 because it's right in the middle of that interval. And our derivative here is just going to be 1 plus 3x squared minus cosine x. And the expression that we're going to use will be x sub n plus 1 is equal to x sub n minus f of x sub n. So 1 plus x sub n plus x sub n cubed minus the sine of x sub n, all over the derivative, which was 1 plus 3x sub n squared minus the cosine of x sub n. We'll type that into our graphing calculator, starting with our first guess of negative 0.5, hitting enter on that, and then we'll use that formula, remembering to use answer instead of the x button, right? So it'll be x sub n minus, use the fraction bar if you can, but if you can't, put the numerator and the denominator in their own parentheses, as well as the whole fraction. And then we have 1 plus, 1 plus x sub n, and then we had plus x sub n cubed, and then we had minus the sine of x sub n, and then that's all divided by 1 plus 3x sub n squared minus the cosine of x sub n. So our first value that we get there actually looks like it's jumped way out of our interval, which it has, but that's okay. So we have negative 1.47937696. And then our next one, in fact, I'm just going to write out a bunch of these because I know how many we're probably going to need here. Kind of a big one here. I think the 7th one here should be the same. So let's see. That was x sub 1. Here's x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, and then x sub 7, which is exactly the same. So I'm going to just write out our last one here, negative 0.9519285,787, just in the interest of saving some time. And I'm going to say you need to write these, because if you don't write those on the test, I'm not going to give you all the points. So we've got them all in the calculator here. Right, they're all there. You can watch them in the video and write them in if you weren't able to get them on your own. But once we got to the 6th one, the 7th one ended up the same. So that is our approximate root for that function on the interval negative 1 to 0. All right, our next one here, we have a cylindrical can that's being manufactured. So I'm just going to immediately start off with a sketch of a cylinder. So here's my cylinder. The cost of the lateral portion, so this part going around, is 15 cents per square inch. So 15 cents per inch squared. And the material for the top is 19 cents, so 19 cents per inch squared. And the material for the base of the can down here is 32 cents per square inch, right? We want the can to have a capacity of 1,000 cubic inches, and we want the dimensions, radius, and height that give us a minimum cost for our manufacture. So we'll start off just by writing out a cost equation. Our cost should be the base, 32, right, times its area, which is pi times the radius squared, so 32 pi r squared, plus the top, which is 19 cents per square inch, so 19 pi r squared, plus the lateral portion, which is 15 cents, times 2 pi r h. And of course, since we're in two different variables here, that becomes a problem. So we need to use the volume, which we know to be pi r squared h, which equals 1,000, right? It says the can has to have a capacity of 1,000 cubic inches. So we can replace the h, which 1,000 over pi r squared, giving us the cost is, well, 32 and 19 should just be 51. So 51 pi r squared plus 30 pi r times h, which is 1,000, over pi r squared. We can cancel out the pi's, and we get our cost is 51 pi r squared plus 30 times 1,000 should be 30,000. And then we have r over r squared, which is r to the negative 1. We need to take a derivative, c prime. That should be 102 pi r minus 30,000 r to the negative 2, or 30,000 over r squared. And we'll want to get a common denominator here of r squared, so we'll multiply by r squared over r squared, which is going to give us c prime is equal to 102 pi r cubed minus 30,000 all over r squared. And when we set this equal to 0, okay, we end up getting, really we're just solving 102 pi r cubed minus 30,000 equals 0. And if you just punch that into your calculator, I'm not going to do the arithmetic on that, but punching that into your calculator tells you that your radius there is equal to 4.54070996 inches, which I'm going to circle for now, even though we're not 100% sure that's actually a minimum. But we can determine that it's a minimum by using our second derivative, if we want, or we can just do a sign chart. Doesn't really matter. If we do, we'll just do a sign chart here. So if we have a sign chart using that 4.54 value and 0 being the minimum for our radius, if we plug in something like 1 into our derivative, we could clearly see that we're going to get a negative. And something more than 4.54, like a billion, we're clearly going to get a positive. So the function decreases, increases. So we are at a minimum. And of course, you can use a second derivative test if you want. Then to find the h value, which we're out of room here, but the h, the height should just be 1,000 over pi times that radius squared, which gives us h is approximately equal to 15.43841296 inches. And of course, I'm using your calculator to find those values, but there's no real calculus to do on the calculator here. We can just use it for approximating those values. All right, on this next one, we've got a square pyramid that's going to have a volume of 500 cubic centimeters. All right, and the volume formula is a squared h over 3 for this square pyramid. So we want to find the dimensions to minimize the surface area of this pyramid, which means to start off with, we need an equation to represent the surface area. So as we do this, first let's sketch out what this pyramid looks like. So, right, it's going to have a square base, and I'll do my best sort of to sort of sketch out what this should look like. Here's the top, and that's mediocre drawing at best, but we've got the side length of the base is a, so those are all a going around, and h is the height of the pyramid, right, which is directly down to the center of the pyramid, right? And so that kind of complicates things for us just a little bit here, because we don't actually have a height for the triangles, right, that are forming this actual pyramid. So we're going to need those heights of the triangles in order to figure out the areas of each of them so that we can find the surface area of the entire thing. So to start off with, we need to figure out and we're going to do it in a different color here. We're going to do it with red. we need to figure out what this length is, which is this right side, this right face of the pyramid. I've drawn the height of the triangle there, so I'm going to call this, we'll call it Z, let's say. And then we've got this distance out here, which should be at a right angle. So we should have a right triangle there, where H is one leg, and then another leg is, this is half of A, and then the hypotenuse should be Z. So we can figure out what Z is using the Pythagorean theorem, right? So 1/2 of A squared plus H squared ought to equal Z squared, right? And so once I have that, I know that Z, in fact, we'll just, we'll write Z is equal to the square root of 1/2 of A squared is A squared over 4 plus H squared. And so now if I take the one face of this triangle that we've got here, or this pyramid, right? One piece of it kind of looks like this, right? Where here is A and here is Z as its height. So its area is just 1/2 of A times Z, which is the square root of A squared over 4 plus H squared. So that's the area of one of those faces. Well, I have 4 of those faces, so 4 of that would just be 2A, right? So 4 of those areas should be 2A root A squared over 4 plus H squared. And then we're going to have to add to that the area of the base, which is just A times A. So I'm going to call the surface area of this pyramid, I'm just going to call it capital S. So we're going to say surface area, which is S, should be equal to A squared, that's the base's area, plus 2A times the square root of A squared over 4 plus H squared. Well, the only problem here is that I don't know what that H is in terms of A, right? So we're going to have to do a little bit of manipulation here to figure out what H is in terms of A. And so the way that we're going to do that is we're just going to go and look at our volume, right? We know that our volume is 500 cubic centimeters. So if our volume is 500, and that equals A squared H over 3, then we should be able to determine that H is equal to 1500 over A squared, which gives us, if we plug that in, our surface area is now A squared plus 2A square root of A squared over 4 plus H squared. Well, H squared, that's 1500 squared, and 1500 squared, well, 15 squared is 225, and then we're going to have to add a bunch of zeros to that, so 225 with 4 zeros on it over A to the 4th. And then it'd be nice to get a common denominator inside of that square root to see if we can simplify down this function. And so that common denominator would be an A to the 4A to the 4th, right? So I'm going to multiply by a 4 here, and a 4 here, and an A to the 4th here, and an A to the 4th here. And 4 times whatever that is, 225,000, is that 2,250,000. If you multiply that by 4, it looks like you should get 9 million. So we end up with S is now equal to A squared plus 2A, and then times the square root of, we've now got A to the 6th plus 9 million, all over a 4A to the 4th. And since we're talking all in terms of positive values of A, I can separate this square root into the top and the bottom. The square root of 4A to the 4th ought to just be 2A squared. So now our surface area is A squared plus 2A times the square root of a to the 6th plus 9 million over the 2a times that square root is all over a 2a squared. Well, I can cancel the 2's, and I can cancel one of the a's, and we then end up with a new function for our surface area, which is probably about as simple as we can hope. Our surface area is equal to a squared plus the square root of a to the 6th plus 9 million all over just an a. And so we want to know when the derivative of this is equal to 0. So we'll take the derivative of this. Right? So when I take the derivative of this, we're just going to get 2a for the first piece of it, and then we'll get a quotient rule here for the second piece of it. So that'll be 2a plus the denominator, a, times the derivative of the numerator, which is 2 root a to the 6th plus 9 million, times the derivative of a to the 6th plus 9 million, which is just 6 a to the 5th, and then plus the derivative of a, which is 1, times the a to the 6th plus 9 million. And then, of course, that's all over, because this was a quotient rule, all over that original denominator squared. And so that should be our derivative. And I put a plus in between there, but this quotient rule should be a minus in between there. That'll screw us up really, really horribly. So if we want to, we can try and simplify this down. I think that's probably a good idea. We can cancel the 6 with the 2, which is just going to make that a 3 instead of a 6. And so we now have, it's easier to plug into our calculator this way to figure out when it equals 0. We're going to have 2a plus, well, let's see, we're going to want to multiply this by root a to the 6th plus 9 million over root a to the 6th plus 9 million, which is just like squaring that one. All right, so now we end up with a 3, it looks like 3, or 2a plus a 3a to the 6th. This is all going to be a fraction here. 3a to the 6th minus the a to the 6th plus 9 million over a squared and then root a to the 6th plus 9 million. Which simplifies just a little bit further into 2a plus 3a to the 6th minus a to the 6th would just be 2a to the 6th minus 9 million over the a squared root a to the 6th plus 9 million. If you want, you can get a common denominator again and combine those things together, but I don't particularly see any reason to do that, because all we're going to do here is we're just going to take that equation and we're going to plug it into our graphing calculator and see when it's equal to 0. Okay? So we'll take our graphing calculator, come back to our window here. We want to graph, and all the a's will just have to be x's. So it'll be 2x plus, and then let's see, what did we have? We had 2x plus, we had a fraction, a big fraction. So I'm going to use the fraction. And if you don't have the ability to do that fraction, remember, put the numerator in its own parentheses, the denominator in its own parentheses, and the whole fraction in its own parentheses. So we have 2x plus, and then in the numerator we have 2x to the 6th minus 9 million over x squared times the square root of x to the 6th plus 9 million. And we'll graph it. And we didn't change our window settings back, so let's just hit zoom, and then option 6, zoom standard. And hopefully we'll be able to see something here. We can see a little bit. It looks like we are going to cross the x-axis somewhere a little past 10. So let's just zoom out a bit. We'll just say zoom, option 3, zoom out. And we'll just zoom out there. And now we can see that our function is negative, negative, negative for a really long time. And then it crosses through the x-axis over there. So we'll hit second, trace, pick option 2, which is 0. And we'll just figure out what that x-intercept is using our calculator. So we go over here till we're a little bit to the left of the x-intercept and hit enter. We'll go till we're a little bit to the right of the x-intercept, hit enter. We'll hit enter again, and we get x is equal to 10.198245. So this is, we'll say s prime equals 0 when a is 10.198.245, and our units were centimeters. And we can sketch a little sign chart here if we want, right? Our sign chart should have 0 for a here, and then it should have 10.198. But if we look at our graph, we know that our derivative was negative, and then our derivative was positive. We don't need to plug values in. Negative means decreasing, positive means increasing. It's clearly at a minimum, which if we look at the problem, we wanted to minimize the surface area. So that's exactly what we were hoping for. We now just need to figure out what the height is because it asked us for the dimensions. The height is 1500 over that a value squared. I'm not going to write that back out. That height comes out to be 14.42249,433 centimeters. And that should be the dimensions that give us the minimum surface area. All right, for our next one here, we're just looking for horizontal and vertical tangent lines for this equation, xy plus 2xy squared minus 2x cubed equals 1. So we're going to start off by taking a derivative, right? So our derivative, we'll use the product rule first, x dy dx plus y. And then the derivative of 2xy squared will be 2x times the derivative of y squared, which is 2y dy dx, plus the derivative of 2x, which is 2 times y squared, and then minus 6x squared is equal to 0. And so from there, we'll just need to solve for dy dx. So we'll gather all the dy dx terms on the left-hand side, everything else to the right. So we'll factor out the dy dx on the left. So dy dx times x plus 4xy is equal to a positive 6x squared when that goes over, minus a 2y squared when that goes over, and then minus a y when that term goes over. So we end up with dy dx is equal to 6x squared minus 2y squared minus y over x plus 4xy. So we need to figure out when this thing is equal to 0 and when this thing is undefined. So it's equal to 0 if 6x squared minus 2y squared minus y is equal to 0. Or in other words, when x is equal to, we add the 2y squared and the y over, right, we get, we'll write 6x squared first. 2y squared plus y, or divide that by 6 to get x squared is equal to 2y squared plus y over 6. And of course, we have to square root that and put a plus or a minus in the front. So that's when we might have horizontal tangent lines, is at those x values. And then we'll have vertical tangent lines, potentially, when x plus 4xy equals 0, right, when it's undefined. So we can factor out the x from that, which gives us x equals 0, and y is equal to negative 1/4. And so we'll have to check those to see if those actually work. So if I put in 0 for x, we get 0 plus 0 minus 0 equals 1. Well, that's not true. So x equals 0 is not in the domain here, so we can just cross that out. So really, we just have the y equals negative 1/4 value to worry about, so we need to plug that into the original equation. So we'll do that. We'll do that on the next page. So when y is equal to negative 1/4, right, the original equation was xy, so that'll be negative 1/4 x, and then it was plus 2x times y squared. Well, y squared is going to be 1/16, and then multiply that by 2, we're going to get 1/8, so that'll be plus 1/8 x. And then we had a minus 2x cubed, which will stay, and an equals 1. Right, so as we plug this into the original, that's what we end up getting. And then we just want to see when is that true. So I'm going to get it all set equal to 0. Right, we'll have 2x cubed if I bring that to the right-hand side. And then a plus 1/4 but minus an 1/8. So a positive 4th minus an 1/8 will be a positive 1/8 x and a plus 1. So we want to know when does 2x cubed plus 1/8 x plus 1 equals 0. So we'll just go back here. We'll put that into our graph. So we're going to type it in. It was 2x to the 3rd plus 1/8 x. You can put your fraction there if you like, 1/8 x or just x over 8, same thing. And then plus 1. And we graph it, and we can find that x-intercept easily enough. I'm going to put our zoom. I'm going to hit option 6, just so we're back to our regular window settings. And we want that x-intercept, so we'll hit second trace, and we'll choose option 2 for 0. We'll hit enter. We'll go find it again, and we'll get 0.767462, negative 0.767462. So there is our vertical tangent line. So we know that that actually solved our original equation. Now we're not 100% certain yet that that did not make our denominator equal to 0. But we could, I mean, if we test that value into that denominator, we would see that that does not make the denominator also equal to 0. And so we can then just not really worry about that. And that's our vertical tangent line. So we have one vertical tangent line. Then we need to go through and deal with our horizontal tangent lines, which means that we were going to take this, the positive or the negative square root of 2y squared plus y over 6, and replace all the x's in our equation with that. And so that's going to get kind of annoying looking, but we'll do it regardless because we need to find these values. So the first term, if I'm going to do the positive square root first, so that's going to be a y, because it was xy, times the square root of 2y squared plus y over 6, so that's the xy. Then we had a 2xy squared, so there's our 2 and the y squared, and then we just have the x attached to it, right? So 2y squared plus y over 6. And then we had a minus 2x cubed, so it'll be minus 2 times that same term, 2y squared plus y over 6 cubed, but also square rooted, so to the 3/2 power, is equal to 1. And so we'll put that into our graphing calculator. So y equals, we'll just replace all the y's in it with x's. So it's going to look like x times the square root of that big fraction that we had, which was 2x squared, or 2y squared, plus x over 6. And then we were going to add to that 2x squared. And then we have that same square root, so square root of the 2x squared plus x over 6. And then we had, again, minus a 2. And then times, and I'm gonna put this in parentheses. So minus 2 times, we now have this fraction, which was 2x squared plus 2x squared plus x over 6. We'll close our parentheses, and then we want to raise that to the power of 3/2. Right? So 1.5 or 3/2, either way. And then we wanted to know when that equaled 1. So we can either subtract 1 from the original equation and look for the x-intercepts, or we can just say graph y equals 1 and look for when they intersect. So we'll graph the two of them. And it looks like pretty clearly there are 2 intersection points. So we'll just calculate those using secant trace. And option 5 is intersect. So we'll start with the one on the left. We'll move to the left of the intersection, hit enter. Move to the right of the intersection, hit enter. And we get, it gave us the one on the right, 0.8693751, probably because I went too far on that y equals 1 value. So then we'll do it again to find the other one. Option 5. Let's go way over here this time. Make sure we don't go too far. And it gave us negative 1.369398. So back here on our other page, we've got our two values, negative 1.369398 and y equals 0.8693971 as two horizontal tangent lines. Then we have to do the same thing again here with a negative of that square root. So it's not really going to change a whole lot. It's just going to change some of these signs. So we have negative y and root 2y squared plus y over 6. And then we're going to have a plus a negative 2y squared times that same square root. And then we're going to have the minus 2 with a negative inside of there, right, being cubed. So it's a negative square root of 2y squared plus y over 6 being cubed. Okay. And we want to know when does that equal 1. And so what we'll do is we'll try and go back to our graphing calculator here and just see if we can sort of adjust this. We needed a negative sign in front of this. So we'll hit second, and then the delete button will insert. So we can insert a negative sign there. So we don't have to retype the whole thing. And then everything else was the same until we got to the plus 2x squared, which ended up being a minus 2x squared. So we'll just change that to a minus sign. And then down here, we did kind of have a little bit of a mess with this. So I'm going to delete out all of this stuff. And so at the end, we had minus 2. And then inside of our parentheses, we had a negative of a square root of the fraction, which was 2x squared plus x over 6. Right, and then we'll close that, that parentheses, right? So there's our half power on it, and then we needed to raise that to the third power, and we want to know when that equals 1. Well, when we look at that, we can see that those two things don't ever intersect. So clearly, this has no solution, and those are our only two horizontal tangent lines. And those values were not going to make our numerator of our derivative equal to 0, which we already saw, because we already found those values. All right, for this next one here, we're just going to do the same thing, finding the horizontal and vertical tangent lines. So first we take our derivative. So our derivative is going to be a derivative of x e to the x should be x times the derivative of e to the x, which is just e to the x, plus the derivative of x, which is 1, times e to the x, and then plus the derivative of x squared, and plus the derivative of y squared, which is 2y dy dx, is all equal to the derivative of 1, which is 0. So we end up with dy dx is just equal to x e to the x plus, well, we're taking those to the other side. It's a negative x e to the x minus an e to the x minus a 2x all over 2y. And so to figure out when this has horizontal tangent lines, right, you could have horizontal tangent lines if negative x e to the x minus e to the x minus 2x equals 0. And it could have vertical tangent lines if 2y is 0, which just means y is 0. For the horizontal tangent line ones, we'll obviously have to plug that into our graph to figure out when that's true in our graphing calculator. But for the y equals 0, we should be able to just plug that back into the original equation, right? If we plug that into the original equation, we get x e to the x plus x squared equals 1. So we just need to graph x e to the x plus x squared and graph 1 and see where they intersect. So we'll do that. We've already got one graph, so we just need to graph x e to the x plus x squared. So x e to the x plus x squared. And if we see when those two intersect, looks like there's two places where they intersect. Second trace, option 5 is intersect. To find the first one, we just go right over here to the left, hit enter, move a little bit to the right, hit enter, and looks like we got negative 1.167586, which we'll write down on the second page in a second here, and then we'll do it for the other one. Which is 0.478174. So we got two vertical tangent lines, x equals negative 1.167586, and x equals 0.478174. All right, so those are our two vertical tangent lines. And then we're going to be looking for our two, or potentially two, maybe more horizontal tangent lines. So we need to figure out when this is equal to 0, right? Negative x e to the x minus e to the x minus 2x. So we'll just go back to our graphing calculator. We'll clear out everything we've got in there. We want to know when does negative x e to the x minus e to the x minus 2x equals 0, so we'll just graph it. It looks like there's one place where that's true. Okay. So second trace, option 2, 0 to find the x-intercept. Make sure you're a little to the left, hit enter. Go a little to the right, hit enter again, and we get negative 0.2752084. Now I'm going to have to plug that back into the original equation for all the x's to find the y. Since these are horizontal tangent lines, they have to be y equals some number. So I'm just going to define this as a variable. I'm going to call it a. And then what I'm going to do is I'm going to go back to my graphing calculator. I'm going to go completely out of the graph, and I'm going to type in that number, negative 0.2752084. And I'm going to hit the STO button with the arrow, which is in the bottom left, just above on, and say alpha, and then the math button, A. I'm going to store that as A in my calculator so that I don't have to type that over and over and over again. So what I want to know then is when does A e to the A plus A squared plus Y squared equal 1. All right, so I'm just plugging that back into the original equation for all the x's. And if I can find when that's true, then I can have my horizontal tangent lines. So I'll just type that into my graphing calculator, but I'll replace the y with an x. And I can either, in fact, this time we'll subtract the 1 over. So really I'm looking for when does a e to the a plus a squared plus y squared minus 1 equals 0. And that way I don't have to graph two functions, and I'll use the 0 function on my graphing calculator. So when I graph this, we'll clear all this out, and what we want is when does, let's see, what was it? It was a e to the a, so alpha a, and then e to the a, so a e to the a plus a squared, and then we can't write the y squared, so we'll do plus x squared, and then it was minus 1, and we want to know when does that equal 0. Well, it looks like it equals 0 at two different locations. we'll use second trace, option 2 for 0 to figure out what they are. First one, as we go to the left and hit enter, then the right and hit enter, then hit enter again, we end up with negative 1.064546. And then for the other one, second trace, option 2 for 0. Go until you're a little to the left, hit enter, a little to the right, hit enter, and we get, looks like positive of the exact same thing, right? And so we'll go back here, and our two horizontal tangent lines are y equals negative 1.064546, and y is equal to positive 1.064546. So we've got our horizontal and our vertical tangent lines. All right, so our next one here, we have a right triangle that's drawn beneath the curve y equals root 16 minus x squared. So first of all, let's sketch the curve y equals root 16 minus x squared. We should know that that's a semicircle with a radius of 4, right? That would be centered at the origin if it was a full circle. So this point right here is the point negative 4, 0. So that's part of our semicircle here, right? Negative 4, 0, the end of it. And that's where the vertex of the right triangle, one of the vertices of the right triangle is going to be. And so our right triangle is going up to some point over here and then dropping down to become a right triangle. And that angle is our angle theta, right? It says the second vertex is at some point x root 16 minus x squared. So that's this point right here. Right? That's the point x root 16 minus x squared. Right? And the third vertex makes the right angle at the point x 0. Right? So that's just the point x comma 0. And so what we want to do is we want to take that point and have it move along the curve so that the x value is increasing at 3 units per minute. So that tells me that dx dt is 3, right? X is increasing. So dx dt is going to be 3. And we want to know how fast the angle is changing when x is 2. So we need to find a way to represent the angle there in terms of that right triangle. And so the easiest way I think for us to do that is just to use the tangent, right? Because the tangent should just be the opposite over the adjacent, right? And so the tangent of theta should be equal to the opposite side length. Well, the opposite side length is just the y value, which is root 16 minus x squared. So the tangent of theta should be root 16 minus x squared divided by the adjacent side, which is, well, it's 4 units to get to here, and then x more units over here. So that'd be 4 plus x, or x plus 4. And that takes into account if the value of x, well, the value of x could be negative, right? So that takes that into account as well, right? Because if it's a negative x value, then that distance, that adjacent side should be less than 4, and a negative x value would take into account that. So all we really need here is for us to just take a derivative here with respect to t. Derivative of tangent theta with respect to t is secant squared theta d theta dt. And then we need to take the derivative of root 16 minus x squared over x plus 4, or over 4 plus x, which just should be a quotient rule problem. It should be the denominator times the derivative of the numerator, which is 1 over 2 root 16 minus x squared times the derivative of 16 minus x squared. So v du minus u, which is root 16 minus x squared times the derivative of v, which is just 1, all over x plus 4 squared. And of course, all of that is multiplied by dx dt. Okay. So really what we need to do is we then just need to figure out the secant of theta so that we can plug that in, because we have the x value and we have the dx dt value. We don't really need to do any simplification yet. but we do need to figure out what the secant squared of theta is at that moment. Well, that's going to be kind of tough for us to do unless we want to use the Pythagorean theorem to find that hypotenuse. So we could do that. The other option is just to recognize that there's a relationship between secant and tangent, right? So we know that the relationship between secant and tangent is 1 plus tangent squared theta is equal to secant squared theta. So I can just replace the secant squared theta with 1 plus tangent squared theta. Well, 1 plus tangent squared theta would just be 1 plus this squared. So we've got 1 plus root 16 minus x squared over 4 plus x squared d theta dt is now equal to all of this stuff right there. And so all we really need to do now is just plug in our value of 2 for x and our value of 3 for dx dt, and then evaluate what d theta dt is. Right, so it's kind of a mess, so we'll do this kind of piece by piece. If x is 2, then we've got 1 plus the square root of 16 minus 4. Right, 16 minus 4 is 12, so we have root 12 over 6. Right, well, root 12 over 6, if I square it, is going to be 12 over 36. Well, that's just 1/3, so this is just 4/3 d theta dt on the left-hand side. So we'll make a new page for that. So we've now got 4/3 d theta dt should be equal to, and then on the other side, well, we had 4 plus x, which would be 4 plus 2. So that's 6, right? That's a 6. And then the negative 2x is negative 2 times 2. That's a negative 4. So that's going to be negative 24 over, and then this is 2 root 12. So we have negative 24 over 2 root 12, which would just be negative 12 over root 12, which would really just be, right, this is negative 12 over root 12, which is really just negative root 12. So we've got equals negative root 12, that's the first piece there. And then minus this, well, negative root 12, and that's going to be minus another root 12. So minus root 12. And then in the denominator, we've got x plus 4. That's just 2 plus 4, that's 6. And 6 squared is 36. And then we have our dx dt, which is 3. So this is over 36 times 3. Well, looks like we end up with 4/3 d theta dt is equal to negative 2 root 12. And then 3 over 36 is just a 12 in the denominator. And if I multiply by 3 and divide by 4, we get d theta dt is equal to negative 6 root 12 over 48. Well, 6 over 48 is just 1/8. So that'd be negative 1 over 8. But root 12, we could simplify that down to 2 root 3. And so we end up with negative root 3 over 4. And I think, I said this was a calculator problem, so you could have let your calculator do all that work if you wanted to. And we could say that's approximately equal to, if we go into here, that's just negative square root of 3 divided by, it's not the divided by 4, and we get negative 0.433 and so on. And these are radians per, this was happening at a per minute, so radians per minute. So if you want the exact answer or if you want a decimal rounded to 3, either way is good. All right, our next one here, we've got a triangle that is drawn underneath the curve 2x squared plus 1 times root 2 plus x minus x squared. Its base stretches from one endpoint of the function to the other, and it's got its vertex angle on f of x, right? So this is just a triangle. We want to find the area of the largest triangle possible here. So we probably don't know what that function looks like. so let's start off by graphing that function, right? We're going to graph 2x squared plus 1, just to give us an idea of what's going on here. 2x squared plus 1, and then times the square root of 2 plus x minus x squared. When we graph that, it looks like that. Now, this is just our calculator having a little bit of trouble resolving this all the way down to the x-axis. I think we could see that if we took the original function, right? In fact, I'm going to kind of sketch this out here. So like we had something that looked like kind of went up, down, back up, and then back down to the x-axis. So it kind of goes up, down, up, down. That's not perfect. But if we factor this out right here, right, we can see that like we could take a negative out of it, right? It's negative x squared minus x minus 2, which factors to negative x minus 2 and x plus 1, which tells us that this is hitting the x-axis at both negative 1 and x equals 2, right? X equals negative 1 and x equals 2. So those are the endpoints of our function, right? 2x squared plus 1 doesn't ever equal 0. It's always positive, so that's not going to yield endpoints of our function. So now what we're looking at is a triangle that has its vertex angle somewhere up there on the function, and it has a base that is, well, that base is always 3 units. So the area of this triangle is 1/2 the base of 3 just times the height of the function, right? Times f of x. So 1/2 of 3 times 2x squared plus 1 times root 2 plus x minus x squared. And we want to do the derivative of that, right? So if I want to do the derivative of that, it's just the derivative of the little function on the inside times 3/2. So a prime will be 3/2, and then times the derivative of that using the product rule, which will be 2x squared plus 1, times the derivative of the root function, root 1 over 2 root 2 plus x minus x squared, times the derivative of 2 plus x minus x squared, which is 1 minus 2x. And then we'll add to that the derivative of 2x squared plus 1, which is 4x, times root 2 plus x minus x squared. And we just want to know, right, we're optimizing this. We want the area of the largest triangle, so we want to know when is that equal to 0. And so we'll figure out when that's equal to 0 just by graphing it in our graphing calculator and finding the x-intercepts. So we'll go to y equals. We'll get rid of that for now. So we had a 3/2 out in front, or a 1.5 was out in front of the whole thing. And then we had a parenthesis with the numerator of this thing starting out as 2x squared plus 1, which was in parentheses. So I should have started with a parenthesis there. See if it'll let me do this. 2x squared plus 1 inside of a parenthesis with the 1 minus 2x next to it being multiplied, and then with a 2 square root of 2 plus x minus x squared in the denominator. And then plus, we had 4x times the square root of that same thing, 2 plus x minus x squared. And we should then close out our parenthesis and graph it. And we see that we've got 3 different x-intercepts. So we'll just calculate each one. Second, calculate our second trace, and then option 2 is 0. We'll look for the furthest left one first, hitting enter here, and then here, which gives us negative 0.687442. We'll write that one down. Negative 0.687442. And we'll look at the next one, second trace, option 2 for the 0 of this. And we'll hit enter just to the left. We'll hit enter just to the right. And we get negative 0.075921. And then looks like there's one more. So we'll do second trace, option 2 again for 0. We'll go ways over here. That's too far. hit enter to the left, hit enter to the right, hit enter a third time, and we get 1.5966959. And we don't have to do a bunch of testing for our sign chart. Because we've got the derivative already graphed. Right? The derivative is positive first, then it's negative, then it's positive, then it's negative. So we're going to go from positive to negative to positive to negative, which tells us the function goes from increasing to decreasing to increasing to decreasing, which means that our maximum area, largest triangle, should either be at negative 0.687 or at 1.5966. So we just need to evaluate the area at both of those numbers. And I'm not going to type all that into the calculator, but the area at negative 0.687442 came out to be 2.67411138. And the area at the other one, which was 1.5966959, came out to be 9.36198841, which is clearly larger than 2.6, and therefore that is our maximum area. Well, area of the largest triangle. That's what it is. All right, the next part of this problem gives us the exact same situation, but this time we've got a particle that's starting at the point -1, 0, moving towards 2, 0, and the value of x is increasing at 2 units per second, so dx dt is 2. We want to know at what rate is the area of the triangle formed by the endpoints of the function and the particle changing when x is 1. So that area is just the exact same function that we had before, right? The area function was just 3/2, that's 1/2 of our base, right, times our height, which was 2x squared plus 1 times root 2 plus x minus x squared. So we're not going to go through and redo the derivative because we just did it, but this time we just want to do it with respect to time. So dA dt should be equal to our derivative, which we, like I said, we already found that derivative. That derivative was 3/2 of 2x squared plus 1 times 1 minus 2x over 2 root 2 plus x minus x squared plus 4x times root 2 plus x minus x squared dx dt now, because we're doing it with respect to t. So if you're not sure how we got that derivative, you can go back to part A and rewatch that, but that's exactly what we did to get that derivative in part A. So we want to find how the area is changing when x is 1 and when dx dt is 2. So we're just going to plug in 1 for x and 2 for dx dt, which is going to give us 3/2. If x is 1, then 2x squared plus 1 is 3. And 1 minus 2 is -1. And then we're going to be over 2 times the square root of 2 plus 1 minus 1, so 2 root 2, plus 4 times that square root again was root 2, and then times the dx dt, which is just 2. We can cancel out the 2's here. And looks like you probably want to get a common denominator here, so we'll multiply by 2 root 2 and by a root 2 and a 2. Right, so that gives us that 3 that's still outside, and now we have -3 in the numerator there, plus 2 times 4 is 8 times another 2, right? Root 2 squared is 2, so 2 times 4 is 8 plus 2, or times 2 is 16, over 2 root 2. And that ends up being, looks like we get 39 over 2 root 2. And these didn't have a specific unit, so we'll just say units squared per second, because we did have a partial unit on there. And of course, if you want to, you can convert that into a decimal or rationalize the denominator there to get 39 root 2 over 4. But I'd take this answer. This answer is perfectly fine. All right, for this next one, we've got the same exact situation, but we want to know at what rate is the angle changing at the point -1, 0, that angle at -1, 0, when x is equal to 1/2. And so I'm going to resketch our picture here. Right? So we had something that kind of looked like this, right? And now we're looking at this angle right here, right, at -1, 0. We'll call that theta. So that's the triangle we're looking at. The height of our function here is just f of x here, right? And when x is equal to 1/2, right, we're definitely over here, right? So this is an x value of 1/2, but we are at a distance here. Our adjacent side to our angle here is just going to be the 1 unit from -1, 0 plus x, however far over we've gone. And so we can turn that into that nice little right triangle so that we can use our trig functions with this. And so our trig functions here, the best trig function I think that we're going to be able to use is just tangent theta. Tangent theta should be the opposite side, which is f of x, or 2x squared plus 1 times root 2 plus x minus x squared, divided by that adjacent side, which is just going to be x plus 1. And so we want to find the derivative here. And so our derivative is going to be secant squared theta d theta dt is equal to the derivative of that somewhat annoying function, because it's, that's pretty irritating function to deal with because it's a quotient rule, but the top requires the product rule. So it's going to be x plus 1, so v, times the derivative of u, so the derivative of our numerator. Well, we actually found that derivative earlier in the other problems. It's just 2x squared plus 1 times 1 minus 2x over 2 root 2 plus x minus x squared, right? Plus the 4x root 2 plus x minus x squared. And then we have to add to that, or actually subtract from that, our 2x squared plus 1 times our root 2 plus x minus x squared times the derivative of x plus 1, which is just 1. And then, of course, that's all over x plus 1 squared. And when we do that, the key thing not to forget here is a dx dt attached to the end of all of this. And so we just want to figure out what this is equal to when x is equal to 1, right? And again, our dx dt that we had previously, what was that dx dt? The dx dt we were using was 2, right? Dx dt was 2. So we're still using dx dt as 2, but now x is 1/2. So we need to evaluate this at that point. And so first we'll deal with the secant squared theta, and I'm not going to probably go through all the arithmetic on this. I guess we could. We probably should. But secant squared we know is 1 plus tangent squared theta, right? And so we know that that's equal to 1 plus the tangent of theta squared, which we had, right? That's this 2x squared plus 1 times root 2 plus x minus x squared over x plus 1 squared. Right? So if we plug in x equals 1/2 into that, right? We'll try to do the left-hand side. We're going to do a new page. We're going to be going back and forth here. So we start off with 1 plus. That's our 1 plus here. And then we have 2x squared plus 1. So if we plug in 1/2 for x, 1/2 squared is 1/4. 2 times 1/4 is 1/2. And 1/2 plus 1 is 3/2. So this piece right here is 3/2. Right? And then this piece in the denominator here, if I do 1 plus 1/2, that's also 3 halves. So those 3 halves are just going to cancel each other out. So really all we've got is whatever's going on with this root 2 plus x minus x squared. Well, that'll be 2 plus 1/2 minus 1/4. Right, well, 2 plus 1/2 minus 1/4 is going to be 9/4. When I square root 9/4 and then square it, I'm still going to just get 9/4. So I end up with 1 plus 9/4 times d theta dt is equal to, now we get to deal with this mess on the other side. So if we put in a 1/2 to, let's start with this term right here, because 1 minus 2 times 1/2, that's 0. So this term is 0, which means all of this is just 0. So I don't have to worry about that. That's really convenient. So I just have the, and then when I'm going to multiply that by this, that's still 0. Right? Oh, sorry, we still need that. We still need that. I was thinking about this one. We don't need this one, which we've already canceled out. So really, in the front, we've got a 3 halves. Right? So, well, actually, no, we don't need that either. So if we think back at our derivative, right, our derivative was v du, right? And so as this, our v times our du was all of this term here, right? So we do need that, right? We have the x plus 1 is a 3 halves, and then times, gotta be careful here, 0 plus, and then this part here is going to be 4 times 1/2, which is 2, and then a 2 times the, it's going to be 2 times the square root of 2 plus x minus x squared, which we already said was the square root of 9/4, so that's 3 halves. So it's 2 times 3 halves, which is 3. And so we've just got 3 halves times 0 plus 3 there for that first part. Right? And then we've got this minus 2x squared plus 1. So 2x squared plus 1, we've already said that is, it's equal to 3 halves, right? Because it's a half squared is a fourth, and 2 times a fourth is a half, and plus 1 is 3 halves. And this is 3 halves, so that's just 3 halves times 3 halves. So we have minus a 3 halves times 3 halves. And then, of course, it's all over x plus 1 squared. And then our x plus 1 is just 3 halves, so 3 halves squared is 9/4. And then, of course, it's all being multiplied by our dx dt, which was just 2. So we've now, hopefully, going to be able to simplify this down. 13/4 d theta dt is equal to 3 halves times 3 is 9 halves. So we got 9 halves minus 9/4 times 2, and divided by 9/4. Right? So 9 halves minus 9/4 should be 9/4. So we've now got 13/4 d theta dt is equal to 9/4 times 2, and then divided by 9/4, which would be the same as times 4/9, which conveniently looks like the 4/9 and the 9/14, or sorry, the 4/9 and the 9/4 should cancel out. We'll just multiply by by 4 to this side and divide by 13, giving us d theta dt. That angle is changing at a rate of 8/13 of a radian per second. So most annoying part of that is just the derivative and the arithmetic on it. That is the final answer there. Just a couple more here to go. So for this one, we're going to inscribe a rectangle under the curve 7x minus 4x squared. So first of all, we need to know what that looks like. That's a parabola that opens down, right? And if we factor an x out of it, right, we can see that it has x-intercepts of 0 and 7/4. So it doesn't really matter exactly what it looks like. It looks something like this, right? Here's 7/4 and here's 0. we're going to inscribe a rectangle underneath it. And just like we did in class, we can call this little distance here x. And since we know that parabolas and rectangles are both symmetric across their midpoints there, right, we know that this distance here is congruent to this distance. So when I take the length here, it should be 7/4 minus 2x. And the height of the function is just, the height of the rectangle is just the height of the function, right, which should just be 7x minus 4x squared, right? And so the area of this rectangle should be 7x minus 4x squared times 7/4 minus 2x. And we want to find the dimensions that maximize the area. So we just need to distribute this out. We'll get a is equal to, let's see here, the negative 4x squared times the negative 2x is going to be 8x cubed. We're going to have a minus 4x squared times a 7/4, which should be a minus 7x squared. And then we're going to have another minus 14x squared. So that'll be a minus 21x squared. And then we're going to have a plus 49/4 x, it looks like. And we want to maximize this, so we'll take the derivative, which gives us 24x squared minus 42x plus 49/4. And so we just want to know, when does that equal 0? I could go through and try and figure that out using the quadratic formula, but that's going to be really irritating. So I'm just going to graph that. So we'll graph y equals, and it was 24x squared minus 42x, and then plus 49/4. And so when we graph that, we can see that it's got two x-intercepts. The first of them, second trace 0, the first of them is that's not. The first of them is 0.3698185. We'll write that one down. So that's when x is 0.3698185. That was it, right? 0.8185, yeah. And then our second one is second trace, option 2 for 0 again. And we'll calculate this other one. Enter to the left, enter to the right, enter again, and we get 1.38018. 1.3801815. And so then we kind of need to think about what's going on here. Well, my domain here is actually just going to be between 0 and 7/8, right? Because I can only go halfway over to 7/4. And this is greater than 7/8, so it's not in the domain. So my maximum area is going to occur here. And we can see that from the sign chart because we just graphed the derivative, right? So if I look at a prime on a sign chart from 0 to 7/8, which by 0.3698 in the middle, right? My derivative was, it was positive over here, and then it was negative, right? So if our derivative goes from positive to negative, our function goes from increasing to decreasing, and our maximum is when x is equal to 0.3698185. It asks for the dimensions, so our dimensions will be 7/4 minus 2 times 0.36981,851, which you can type into your calculator, but I'm not going to do that. For you, it's 1.01036,298. And the other dimension was the height, which was 7 times our x value, 0.36981,851, minus 4 times that same number squared, which came out to be 2.04 1.6666649. And we had no units in this, so you don't need to bother with units. Those are our dimensions. All right, our second to last question here. We're going to inscribe a rectangle under the curve root 9 minus x squared. And for this one, I don't think we're actually going to need a calculator here, so we'll try and do this one without the calculator. The function is just that semicircle, right? And when we inscribe the rectangle underneath it, we should see that the length should be double whatever we go over x, right? Those are the same. Those are congruent. So our length is 2x, and our height, or our width, whatever we want to call it, we'll call it the width, is equal to the y value at x, which is just root 9 minus x squared. So our area function here should just be 2x root 9 minus x squared. And if we take the derivative of that, we get a prime is equal to 2x times the derivative of root 9 minus x squared, which is 1 over 2 root 9 minus x squared, times the derivative of 9 minus x squared, which is just negative 2x, and then plus the derivative of 2x, which is 2, times root 9 minus x squared. If we get a common denominator, which we can cancel these 2's, so we'll get our common denominator of root 9 minus x squared, which means we're just squaring that, then we should see that we end up with a prime is equal to negative 2x squared plus 2 times 9 minus x squared, all over root 9 minus x squared. Or if we simplify that down, it's just going to be 18 minus 4x squared over root 9 minus, over root 9 minus x squared. We'll set this equal to 0, and we see that that equals 0 when 18 minus 4x squared equals 0. Well, that would be when x squared is equal to 9 halves, or when x is equal to plus or minus 3 over root 2. Obviously, 3 over root 2 is our only option, not negative 3 over root 2. We're not going to have an x value of negative 3 over root 2. So x is going to be that. We should prove that it's a maximum, right? So we're going to put 0 on here. Here's our 3 over root 2 value. And the furthest we can actually go over here is going to be 3. So we'll put that as the kind of end cap on our sign chart. And if we plug in something like 1, right, that gives us a positive in our derivative. And we plug in something between 3 over root 2 and 3, we get a negative. So we increase to decrease. It is a maximum. Our length is 6 over root 2, and our width is the square root of 9 minus x squared, which was 9 halves. 9 minus 9 halves is 9 halves. So the square root of 9 halves is 3 over root 2. So we have a length of 6 over root 2 and a width of 3 over root 2. All right, here is our last equation. We are looking at the function 1 plus cosine 2x, and we want to maximize the area of a rectangle that can be inscribed under one arch of this. Now, you should know what this looks like, this function looks like, without graphing it, but just to make sure, we're going to look at it here. If we graph 1 plus cosine of 2x, we should see that it just looks like the cosine of 2x function, right? It's going to have a shrunken down period, or a larger frequency of the waves, and it's going to be moved up 1 unit. And so one oscillation of this should go from wherever that x-intercept is. Well, you can use your calculator to find those x-intercepts if you want. Actually, you actually won't be able to do that because it doesn't cross through. So you can only do that when it crosses through. So we can't actually do that. So what we need to do is we need to figure out when does 1 plus cosine 2x equal 0. And so that would be when the cosine of 2x is equal to negative 1. Well, the cosine of 2x is equal to negative 1 whenever that angle is equal to pi, right? So 2x needs to equal pi plus 2 pi n. Right? And so if we divide everything by 2, we get x is equal to pi over 2 plus pi n, which gives us, when n is 0, pi over 2. And to make this easier, we're going to go backwards and put in n equals -1. That gives us x equals negative pi over 2. And the reason I'm choosing to do that is so that I can sketch the portion of my curve that goes from here to here. So that when I sketch my rectangle in, right, the distance here is a distance x. If I were to sketch it from pi over 2 to 3 pi over 2, then I'm all messed up with my x distances here. And so it's going to be much easier to do it this way. So our length is going to be 2x, because these are going to be congruent segments. And our height is just going to be 1 plus cosine 2x, just like the last problem was. So our area function is 2x times 1 plus the cosine of 2x. We can take the derivative of this. Right? So a prime is just going to be the first function, 2x, times the derivative of 1 plus cosine 2x, which is, using the chain rule, -2 sine 2x. And then plus the derivative of 2x, which is 2, times 1 plus the cosine of 2x. And we just want to know, when does that equal 0? And we want to know, when is it equal to 0 between x equals 0 and x equals pi over 2, right? So that's really the only interval that we are interested in. So I'm just going to type that function into my graphing calculator. I don't need this one anymore. I'm going to do 2x times -2 sine 2x. And then I'm going to add to that 2 times 1 plus the cosine of 2x. And when I graph that, we've got all kinds of x-intercepts, but we only want the ones between 0 and pi over 2. So we'll do window, and we'll change our x minimum to 0 and our x maximum to pi over 2, so that that's all we're looking at on our graph. And so we can see that there is only one critical value there. We'll do second trace, 0, to find it. Hit enter there. Go to the right till we're to the right of it. Hit enter. Oh, it's gone way too far. Hit enter again. And we end up with 0.6532712. So that's our x-intercept. So this equals 0. So we'll do this on a new page. We've got a prime is equal to 0 when x is 0.6532712. And we saw from our sign chart, right? We can make a sign chart, 0 and 0.653 and pi over 2, that the derivative is positive over here. Then the derivative is negative to the right of that x-intercept. So our function increases, then decreases, telling us we do have a maximum at 0.653. So we'll call this, we'll just define this as b, and our length, which was 2x, should just be 2b, which is equal to 1.3065 4 4. And then our height, which was 1 plus the cosine of 2b, should be equal to 1.261189185. And those are the dimensions that give us the largest rectangle inscribed underneath that cosine curve. And that is the end of our walkthrough for the applications of derivative extra practice midterm review. So that is all for your midterm reviews. There are 5 different midterm reviews. I suggest that you do all of them before the midterm, and hopefully this was helpful.